participants that the attendance uploading is in progress. So kindly give us some time. There is a lot of mismatch between the names on the portal and the names that are coming up in the attendance through Google Meet. Also, there is a lot of mismatch between the email IDs on the portal and the email IDs the participants are using to log in. Because of this mismatch, it is this uploading is taking a lot of time. So I thank you for being patient with this, and we will keep uploading it on as early as possible. So kindly do not panic if you do not find your attendance on the portal. This is taking a lot of time because of the mismatch between the surnames and the email IDs and so on. So thank you for your cooperation. Okay, so I see that Dr. Devayan has joined us. So good evening, Dr. Devayan.
Hey ma'am, how are you doing?
I'm good. I'm good. If you give me 2 minutes to briefly introduce you to our participants, okay, so just allow me like 2 minutes. Is the screen visible, Nikunj? Is the screen visible?
Yes, yes,
Okay.
Vijay.
All right. So Nikunj, can you start the recording also, please? Has it started?
Some people will be removed from the meeting due to technical.
You can remove them. You can ask them to join again.
Uh-huh. Okay.
Yeah.
Okay. Yes, madam. I guess the recording has been started.
Okay. So we welcome all participants to this seventh session on this FDP on deep learning for vision and language. Today's session will be by Dr. Debayan Deb, who is Chief AI Scientist at Tech5, and he's the CEO of Lens Corporation. The title of the today's talk is Deep Learning, Innovations in Low Latency AI Powered Video Management Systems. And here's a brief about Dr. Debayan Deb. He's a visionary AI entrepreneur and biometrics expert, specializing in developing cutting edge solutions at the intersection of deep learning, computer vision, and identity recognition. Dr. Deb has led pioneering innovations
Madam, your
in
voice
low
is breaking
latency
in
AI
between.
powered video management
Hello.
systems. Dr. Deb has led pioneering. Oh, is it clear now? No? Hello?
Yes, 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 yes. It is clear now. Yes,
It's clear? Okay.
yes,
So
yes.
maybe I'll start again. Dr. Debayan Deb is a visionary AI entrepreneur and biometrics expert, specializing in developing cutting edge solutions at the intersection of deep learning, computer vision, and identity recognition. As the founder and CEO of Lens Corporation, Dr. Deb has led pioneering innovations in low latency AI powered video management systems and advanced biometric solutions for real world applications. Dr. Deb holds a PhD in biometrics from Michigan State University under the mentorship of the renowned Dr. Anil Kumar Jain. his recent emphasis on ethical and trustworthy AI development. With Lens Corporation, Dr. Dev has been solving some of the most challenging AI ML problems, including real time video surveillance, face recognition, and intelligent access control systems. An advocate for explainable AI and impactful innovation, Dr. Dev regularly collaborates with industry leaders and academic institutions to drive research and development in emerging technologies. His flagship product, LensView, is a next generation video management software transforming the surveillance industry with AI driven insights and seamless user experiences. Dr. Dev is also deeply passionate about education and has delivered expert lectures globally, inspiring the next generation of researchers and technologists. So, Dr. Dev, we are really grateful for you to have joined us today. We know you have a very hectic schedule, and we are honored to have you here. So, over to you now for your session.
Thank you, ma'am. Thank you so much for having me. Thank you, everyone, for joining. I'm very, very excited to showcase some of the work that we have been doing and the kind of challenges that we face, on a daily basis, especially in the field of digital identity, and also known as biometrics, more technically. I will, without knowing each and every one of you and let's say, the depth of knowledge within biometrics, I'm going to keep it at a very high level, but I'd be happy to answer any, technical questions that you may have. So to start out with, I'd like to first introduce my company Lens, where we do a lot of advanced artificial intelligence work, especially in the domain of security. And the idea behind Lens has always been to, question the status quo and push the boundaries to, find cutting edge solutions. So not just, take anything off the shelf AI model and just apply. The more important thing is, are we able to, handle all these edge cases that we see in the real world? Some of which you will see, it's very, very niche problems. But these are the problems that have been left out by a lot of industry professionals in the past. So we offer best-in-class AI solutions that are very, very fast and efficient, can be also run on small compute devices. And we really prioritize, first and foremost, explainability, transparency, and very easily customizable AI solutions. So just a brief about our company. We started in 2016. I was doing my PhD under Professor Anil Jain, as Dr. Preeti mentioned, at Michigan State University. My dissertation and thesis has been on, again, biometrics primarily. And I have a few, papers that we published and has pretty good citations so far. And my co-founder, Ashri, he has a background in Salesforce and mobile development. He is our COO, and he works through a lot of the operational items at Lens. And some of our clients, this is a very brief subset of a few of our clients globally. Some are in US, some in Europe. There's a few in India as well. So we work with quite vast clientele in the field of security. So I would like to first introduce and motivate the problem at hand and why we need biometrics. Of course, much of it is very obvious. The biggest issue is that over the years, people have transformed from things like passcodes and passphrases to not being able to trust who has certain information. The one thing that ideally does not change is who you are, which is where the biometrics part comes from. Things like your fingerprints, your iris, your face, other physical characteristics all form something called as biometrics. And also in airports, I'm sure you see that, especially in India, we have the largest biometric system in the world, which is Aadhaar. So we have been very much used to, let's say now, using biometrics on a regular basis. And then, of course, other than that, there's a lot of security concerns that biometrics solves, which is ID documents used to be the way to go a long time ago. But then, of course, as we know, these gets lost or even forged, whereas biometrics is a lot harder to bypass. So in biometric recognition, there have been many years of research behind it, and many folks and researchers have proposed a lot of different physical traits that can be used. And traits are basically like face, iris, fingerprints are the three most widely used. But then you also have things like voice, your palm, other vein patterns inside your body that you can get from infrared cameras, your thermal signature, your signature itself, the way you type, things like that. So these can all form some sort of identity, features that we can utilize to say you are either divine or you're not, right? So the word biometrics comes from life, and metron, which means measure. So you're measuring life in some certain way. So some of the applications that are used, and something that we have been, part of as well is iris recognition has been a very big part of Lens. We will go through how we solved a lot of problems using iris. So that is very commonly now used in a lot of mines where your face is, greasy. There's a lot of oil and marks that you get. So using face is not a very, good trait, and the same thing with fingerprints. You have a lot of dirt that's there. So iris has been a very popular way to identify who the worker is. And similarly, in a lot of turnstiles, so these are the entry systems that you see everywhere in office buildings. We worked in the past with Walt Disney's theme parks, where we had these fingerprint models that we deployed for them. So, I'll just give a very high level summary of how a biometric system works. So at the end of the day, we want to have two different modes of any biometric system. So either you're trying to authenticate yourself or you're trying to do any sort of search. Authentication here means that you present two images of or two samples of your biometrics. So let's say I have my face taken like 10 years back, and now I have a new face today. I want to see if these two faces belong to the same person or not. So I'm just authenticating that, I'm divine. And then there's searching. This is operationally different. So I'm submitting one image of myself, and I'm comparing this image against a whole gallery of many different people that are enrolled into the database. I want to figure out who this person is. So in summary, authentication means, is it the same person or not? And search involves the question of who is this person? So search is more like identification. So we just briefly spoke on the traits. Again, the three most popular are, as we all know, fingerprints, face, and iris, which is also commonly used for, let's say, enrolling in Aadhaar, for example. And so there's also a lot of, legacy databases, which also helps propel a lot of these algorithms, especially on the deep learning side. As we know that most of the deep learning approaches are very data hungry approaches. So you need tons of data. That's another reason why these three traits are super popular, because there is still some availability of data on these three traits. And currently, there is the largest evaluation is done by the US government. So every year or every so years, the NIST, the National Institute of Standards and Technology, they evaluate who are the best vendors that are building these biometric algorithms. So there's a whole competition that happens. So the current results, as you can see on the slide, fingerprint, iris, and face are all, they all perform really well. So TAR here, you can think of that as an accuracy metric in terms of, how it's more like the verification, authentication part that I said. So you're matching two images if they're belonging to the same person or not. So what's the accuracy of that? And the more stable biometric out of these that we have also found in practice is usually iris. But there's a lot of things going for fingerprint as well. Face is very unstable, and there are a lot of challenges that we face on face, let's say. I also work with quite a few biometric companies. I, lead some of their R&D. Our largest client in this space is Tech5, and we broke a lot of records from them. So I lead their research and development team. So the Tech5's fingerprint and iris matching algorithms that me and my team created together is the fastest in the world currently. Also, it's on the top 5 rankings as well. So we can start with, trying to understand a bit more on how traditionally, let's say, something like iris recognition we used to do. So in the past, the most common algorithm for iris, for example, used to be to take so basically, first, let me explain what the iris region is. So if you see the image on the bottom left, there are 3 major parts to an eye. So one would be the pupil region, which is the really dark region in the middle. And then you will see that there is a band, 2 concentric circles around it. So that band, all that's inside is the iris of the eye. And everything outside, the white regions, are sclera. And all these 3 things can actually be used for recognizing you. But the iris tends to be a lot more discriminative to say who is Divine, who's someone else, so on and so forth. So our goal is to use this band in the middle, the grayish region that you see, and identify very unique features that make me who I am in some sense. So traditionally, how people used to do this is to first detect, using Huff transforms. There's many methods to do this, but you basically try to detect or fit a circle that first fits inside the pupil. So the idea is very basic traditional methods, like you find the darkest spots, which is most likely the pupil in the eye. And then you do a connected component analysis to figure out what all pixels are clustered together. And then you fit a circle around it. So that would be your pupil. And then so on and so forth. You go to the next circle, try to find the boundary of the iris itself. So once you have these 2 circles, if you refer to the image on the top, what we try to do in a high level is to basically try to cut from one plane and sort of unwrap this entire iris into a flat sheet, which is why it's called a rubber sheet model. So we go from the polar coordinate system to the normal Cartesian coordinates, as we are more familiar with. So once you unwrap it, it's a lot easier for algorithms to find patterns in general. And that's what you see in the bottom. So this is an actual unwrapped iris. And then what you would do on top of that is to find, using very traditional like Gabor filters, there's lots of different filtering you can do to find features that are making these unique. So this has been a very common technique to do iris recognition for many, many years. And we, along with a few researchers, but at Lens, we were among the first from industry to propose using deep learning. And we had incredible results doing so. Why deep learning? There are many, many points around it. As we know, like most of the performance benefits of deep learning that we get from something like here, where we think, for example, just the iris region is important, but we don't know if that is the true story. Maybe the pupil together with the iris could be important. Maybe our eyelashes also have a pattern in them, so on and so forth. So our idea was to take the entire image and maybe train a convolutional neural net and then see how it performs. So that's how we started it. Very similar to how you would do face recognition and others. But the challenges was, how do you sort of combine first left and right iris together into one model, ideally. And then the other aspect has been how to improve performance, as always, the accuracy of matching, right? So that was one aspect. The other aspect was we also tried to combine the raw image, which is not the unwrapped one, the whole eye, along with the unwrapped iris to see if there's some potential performance benefits as well. So there's a lot of ensemble of different deep learning models that we came up with, and some, custom, let's say, loss functions as well that we came up with. It's a combination of triplet loss and a few others like arc face and so on and so forth. So that was one aspect of it. The other aspect now that we're working on towards, so we sort of are very happy with the performances on Iris. As I said, it's a very stable biometric. There's very little variations that we see in terms of challenges. But then what we're now pushing more towards is that getting Iris data is the hardest challenge because it's a very invasive way to collect your biometric. So literally you have these goggles that you put on your eye, and then there's two large flashes of light that shine on your eye region. So it's a very invasive technique to collect data. So, and of course, you can't just go on Google or scrape the internet to find iris images either. It's very difficult to find iris images off of that. So our idea has now shifted a bit more towards, why don't we try to generate a lot of irises where we can also make sure that each iris image we're generating, we can control the identity of the person. So whatever we saw here with deep learning, we are trying to find a way of using the features learned by a convolutional neural net and use those features to make sure we can control an image generation. This we can synthesize the iris back so that we can generate more images of the same identity. And that way we can, expand our current data set in terms of, horizontally. So we have, let's say, 10,000 subjects of, 10,000 people's data. And then you can have, millions of images per person, for example. That's one challenge. The other challenge is to also expand the database vertically, so have new people that don't exist. And this would, propel us to go to a new future in biometrics, which is trying to train these models without invading anyone's privacy. And that is something I'm very excited about in our field because I feel like that should be the way to go, where imagine a scenario where you use very few people's biometric data to train these large, deep learning models with mostly just synthesized images of people that do not potentially exist in the world. And then you're able to deploy it and the performance is still very good. So that is the biggest goal that we have there. And so we can now switch gears, let's say, to more of the fingerprint side of things. So very similar to Iris, we also had a lot of traditional methods that were proposed for identifying people based on their fingerprints. The most common method has been to use something called minutia points. So I would urge all of you to take a look at one of your maybe your index fingers, fingerprints. If you can, really zoom in to your finger, you'll see that there are many different patterns. So the most obvious pattern is, of course, the fingerprint ridge, which are these valleys and ridges that you will see. But then the more interesting thing than the pattern of these ridges themselves is the fact that sometimes these ridges break apart into two ridges. It's called a minutia bifurcation. And then at the same time, you will see there are some minutia points, which are basically two ridges that are collapsed into one. So you have all these singularity points, as they're called, or minutia points. There are many names for this, where these form sort of a very unique pattern that is extremely unique to not just yourself, but also potentially, or at least that's what people have claimed, is that it's very unique to your finger itself. So you can then store these minutia points along the entire fingerprints. And then when there's a new fingerprint that comes, you can then use graph-based matching to see how similar are these two sets of minutia points. So this has been an extremely common technique for a very, very long time. But there are multiple challenges that you will start facing once you go into this kind of an approach. The largest challenge is, for instance, so your number of minutia points. So these are how many times the ridge is splitting, where they're splitting, which angle they're splitting, so on and so forth. But the number of these unique points vary from finger to finger. It also varies based on how much pressure you're applying onto the fingerprint reader, as well as a few other factors like the lighting, so on and so forth, because sometimes these algorithms could miss a few fingerprint points, like these minutia points, once in a while. So now you have varying number of points, so it's a very difficult way to match. You have to find a subset that has some probability assigned to it to say, I think this is 60% the same fingerprint, graph or not. But the other problem is, as I said, it's varying. So the number of points change from instance to instance, finger to finger, and person to person. The problem with this is that when, let's say, we were talking earlier about searching, for example, so we have 10 fingerprints per person. And then let's say we have, 2 billion population in India, for instance, then you'll have, close to 20 billion fingerprints, but even there, each finger has its own variation. So it could be 10 or 15 more. So now we have to store all of that into a massive database across, I don't know, hundreds and hundreds of computers, right? So that is a very big challenge. It's very expensive. And now doing matching on top of that, when a new fingerprint arrives, that would take a significant amount of time to do. So what is a solution for this was where I started asking this question, which is there even a solution? Let's say, can we go beyond just minutia points? The answer is always deep learning, right? So there are a few huge advantages that, we had a huge breakthrough doing it this way. Using convolutional neural nets again, because the first insane advantage you're getting with this is that, let's say you have a bunch of convolutional layers, and then at the end, if you have a fully connected layer, for example, you will always get a fixed dimension feature vector, right? And then this dimension you can set once, but it will be the same for every single image that you pass to it. So say 128 dimensional feature vector. So in other words, there are 128 features that are describing one image. But this will be fixed forever. So your matching speed, the storage size, the computation times, all those reduce significantly. So this is a huge advantage that you can get. But what we found is that we also have some more advantages using deep learning in this context, in fingerprints specifically, where you can also combine. The convolutional neural net in itself, one of the biggest challenges we have with AI today in general, and CNNs especially, is that we almost have very little idea on what kind of features it's looking at. So it is possible that it's looking at a lot of these minutia points anyway internally, but it could be picking up on a lot of other features, which we, colloquially, we're just going to call them as, let's say, texture features. So it's possible that it's looking at a lot of the texture. So like if you have a cut in your finger or other kinds of, features like that, it could be using that as well. So the one amazing approach that we took is that we made two different models first, where we first force it to just use these minutia points to do the matching part. So just look at all the minutia sets that you get from each person, convert that into an image that the deep learning model can understand, and not show it any of the fingerprint pattern or anything like that, just the minutia points, right? So we encode those into a feature vector and then do the matching. So we get, let's say, a certain kind of accuracy there. It's also very, very good compared to using just the traditional methods. Then we tried using the entire image, very similar to the raw iris. So I hope like you're seeing a pattern into where I'm going to go with this, which is, yeah, and then we look at, let's say, the raw image, pass that through the model, you get some other kinds of features, let's call them texture features, and then you're combining both of them together to get your final performance, which beats, let's say, just minutiae or just texture features. So the idea is very, very similar, let's say, from iris in some sense, where you want to also utilize some of the, efforts that the prior research has done, because previously people have handcrafted these features and the performance has been very good. But you also want to augment with deep learning and try to combine these two ideas. So you take domain knowledge and then you take whatever these AI models are learning, combine them together in some sense. And then that performance usually outperforms either one of those approaches in general. So before I move to the next part, I'd like to take some questions or any insights or anything you guys may have.
Participants, in case you want to interact with Dr. Deb, please kindly unmute yourself. I think there are no questions right now, Dr. Deb. We can continue.
Sure. So this was so far about iris and fingerprint, and just to top it all off, I'd like to also, as I mentioned earlier, we participate in NIST through Tech 5. As you can see, the current results, we're in the top 5, I believe, here. But now we're, I think, on number 3, if I'm not mistaken. So we're continuously pushing the boundaries, and trying to improve these performances. And then the way we do that is not just, simply apply, let's say, a ResNet 50 model at, a huge data set. While that has its merits, but I can guarantee you in these, let's say, NIST evaluations, for example, where you have other companies working for the last 40, 45 years, they have handcrafted each and every one of their solutions. It's not going to be an easy task to just beat them by just throwing a bunch of data at a large model. You have to also consider what are the traditional methods, take that into account, and apply a lot of these domain knowledges into it. So, and again, a few more patents that we've done on the biometric side. And then there's a few papers if you like to refer and take a look at some of my work in the past in this domain. Please feel free. We did a lot of work in India, actually. So I can start with some of the more interesting applications. As I said, performance, accuracy, everything is one thing. So the story behind Lens is very similar to what I actually faced. Was in academia, I was more focused on, just improving, let's say, the recognition performance. Can we identify two people, two images of a person or not, so on and so forth, right? So all the time, each and every one of my paper is building on top of improving my prior paper, right? But at the end of the day, I realized that, okay, so that's very good, but also, are we taking into account each and every human we're able to make this work, right? And this question was not asked by quite a few people, surprisingly. So when we look at something like, let's say, something like this, right? Like when we are looking at these accuracies, while on the onset, it's really, really high. We also have to see where they're failing at the end of the day. So they are still failing. They're not 100%, of course. Number one. And number two is we also have to account for, there's a lot of bias on which data sets you're testing on. So a lot of these data sets, since they are organized by the US government, they are very heavily catered towards a certain demographic, which may not work for the rest of the world, especially the part of the world that actually needs to have very good digital identity because of fraud, because of losing identity documents, so on and so forth. So in essence, even if you're pushing these accuracy numbers on NIST, does it really solve the problem at least I set out to solve, which is to make sure everyone has some sort of digital identity at some point, right? So then we have to consider what are these limitations of all these biometric systems that we see today, right? So, for example, one area of research that we found was that infants and people younger than a certain age, for instance, they have very underdeveloped fingerprint ridges. So traditionally, you couldn't identify someone based on the traditional algorithms below the age of 3 years, until their fingerprint is fully developed. But then, of course, you can have more high resolution cameras now. You can have more sophisticated algorithms to do matching. For example, deep learning is a very good example of that. So if you have even underdeveloped ridges, for instance, I mentioned earlier, if you not just look at the minutia points, but also look at the texture features. So even if it's underdeveloped, that's still a pattern, right? How much it developed, so on and so forth. So why not use that and see if you can match someone who's even below the age of 3. And that's essentially one huge giant, kind of work that we started, which is infant identification. The other line of work was on people who, intentionally alter fingerprints. So this happens quite frequently with criminals, where they either burn off their fingerprints, or even more disturbingly is that they take fingerprints from another finger, stitch it in, and so on and so forth. So there's a lot of weird stuff that people do. But the idea is, can we still match them at the end of the day, right? So again, using something like a deep learning method is the only way to achieve that. And thirdly, there's a very specific niche of, let's say, people who are enrolled in Aadhaar. There's a lot of manual laborers, as well as people that do construction or work with a lot of chemicals. They have eroded fingerprints. So most of the fingerprint recognition systems at that point, I think close to 2017, 2018, when I was, evaluating a lot of these fingerprint matchers that exist from other vendors, most of them failed when it came to eroded fingerprints, or some parts are disappeared, so on and so forth, because of chemical use, other kinds of manual work. So that's another huge population that people have just completely left out, because again, the general population, the accuracy numbers are really, really good. But my more interest was on these little pockets that are being left out, and how do we tackle those problems. So infant ID, as I mentioned, was one of the first step towards this. So we looked at even more features than minutia. We identified there are core points, there are valleys, ridges, pores. We pass all these information in to a large AI model that takes into account all of these handcrafted features that we identified for infants, along with the traditional, what I said, the texture-based matching, that matcher that I talked about earlier. There's also a concept that we introduced, which is also scaling the fingerprint image itself based on the age of the infant, because that is something we can have at least estimate based on the fingerprint itself. So let's say in this case, we have a 6-hour-old baby. So his or her fingerprint can be scaled at a certain, like, let's say, pixels per inch that matches an adult's fingerprint. So that way, when he or she grows and becomes an adult, the scale of the fingerprint will remain similar. And so this also helps having a very good matching performance when we match a infant as they're growing. So this was a very interesting line of work that we worked on.
Dr.
And so
Big,
we, yes,
excuse me. There is a
yes.
question. Parul
Oh, sure.
Khandelwal wants to interact with you. Parul?
Please go
Yes,
ahead.
ma'am. Hello, sir. Sir, I just wanted to know in this that you have mentioned that you are using the texture features also along with the minutiae features in
Mhm.
this fingerprint recognition. So, what are these ridges, pores, core? Are you considering them as a texture features, or there are some other features?
No, actually, so that's a very good question, actually. So in these cases, we actually handcrafted. So we say like minutia is one kind of feature, core is another kind of feature, valley is another kind of feature, and ridges and pores are different kinds of features. Texture is everything that we're not, handcrafting and telling the model anything. So everything else here that you see, for example, like the color information, which is in grayscale, I know, but the contrast of the fingerprint, how it erodes on the top, those are what we call as texture features here.
Okay.
Hope that helps. Yeah.
Okay. Okay, sir.
Mhm.
Thank you.
Thank you. Um, so, okay. Just give me 1 second, Dr. Preeti, if you don't mind.
Sure.
Just I'll be back in a second. Yeah. Sorry, I'm had a quick call. So yeah, I'll resume the lecture. So now we are going to move into how do you collect these fingerprint images. So I don't know if you realized it, but this fingerprint image, for example, the color information, how gray it is, so on and so forth, is very, very different from, and even this fingerprint, this is of a baby on the bottom right. It differs a lot from something like this, right? So this is a grown adult's fingerprint taken from a standard off-the-shelf fingerprint reader. So it's very different. If you look at the color information, there's space between the two ridges, everything is vastly different. The reason behind that is that, again, if we use a traditional fingerprint reader, they do not, for most part, collecting the infant's fingerprint is itself a very difficult task. But also these sensors do not have enough resolution camera to capture all these pores and ridges and so on and so forth for an infant. They're too young, it's not developed well. So the information is just not there on a traditional sensor that has like a 500 PPI camera, usually pixels per inch. That's their resolution. So it's very, very low. So instead, we built our own fingerprint reader from scratch using, just very simple Raspberry Pi, small little computer that we procured, and then we built a whole 3D model, 3D printed, casing around it, and made it very convenient for anyone to just slide an infant's thumb onto it. And it captures at 2100 PPI. So it's significantly larger resolution information that we can capture from it. And then the second task was, so of course, let's say you're able to now collect very good, high resolution image from an infant, and perhaps you're even able to match this very high resolution image to the same infant after, a year or two, for example. But now the question is, what happens when they have to get enrolled into something like ATAL, right? Where they have these traditional fingerprint readers. So do you have to now go again and re-enroll yourself? That was a major question that, UIDAI was asking at the end of the day. So then we had to develop another model that then takes these fingerprints. As I said, the scaling was one aspect, but we also have a generative AI model that takes these images. So an image to image model takes these images, translates them to something that looks like these standard traditional fingerprint images. And if that works, then we basically use that for the rest of his or her lifetime. So basically, again, we transform these high resolution custom, infant fingerprints to an adult one at some point as they're growing. So that has been another interesting work at Lens. And we have been able to demonstrate that this works. Now, will it be in full production is another question at some point, but it's a really, really cool way to, again, as you see, the pattern is to make sure that no one gets left out, but also make sure that operationally everything is, aligned. So the whole, research behind biometrics is not just, again, to improve performance, but also to make sure everything is operationally valid, as well as it's going to work with existing systems. So it cannot be every day you come up with a new, even deep learning models change significantly, as we know. There's so much growth there. But then imagine a scenario where if we enroll each and every Indian citizen, their data into Aadhaar, we will get all their templates, features, whatever you want to call that, and we store that into a database, right? And then tomorrow, if you tell the Indian government, for example, we now have a new fingerprint recognition system, you now have to re-enroll each and every person's fingerprint all over again, because these templates and features change rapidly from model to model, right? So there's a very delicate balance you have to maintain. So for that purpose, we, as I mentioned, have our own infant fingerprint reader. And so, it's a very, very compact reader. It has very high resolution camera inside it. And it can be made at a very, very low cost. So the cost is around $45. But of course, if you mass produce it, it's going to be a lot cheaper than that. And then it's also very ergonomic. So as you see, the glass platen is sticking out of the box. So you just slide the box onto the infant's thumb and it immediately captures. So we also have mechanisms to detect if there's a fingerprint that's there, if the quality is good, and it just automatically captures it. We don't have to pressurize the thumb or anything like that. And there's also less motion blur doing it in this manner. Okay, so before, again, I move to Face, I'd like to take some questions because now it's going to change into a very different direction, let's say. If there's any.
One more question I have.
Yes.
Can you go back to one slide back?
Yes. Mm-hmm.
One more slide.
One more, okay.
Uh, One more. Sorry.
Okay. No worries. Yes.
Yeah. Here you have mentioned that maybe you find it silly, but I'm not able to uh, imagine this thing. Like you have said that fingerprints, the paper which you have mentioned over here is fingerprints for reducing infant mortality. So
Yes.
how fingerprints are helping to reduce the mortality? I'm not getting it very correct. Matlab, like how this is helping in this.
Okay, so there's a lot of aspects where it directly affects infant mortality. I should have also mentioned those points. So the first big application, let's say, before even going into the mortality situation, there's a lot of crime that happens. Primarily, there is a lot of not just crime, but let's start with the most simple case, which is baby swapping. This happens quite frequently in hospitals. So you accidentally take someone else's baby and so on and so forth, right? So this is one way to stop it. So right now, what they do is they have a tag around the person's, the baby's, wrists. And then there's a number associated with it. So sort of like an ID that you assign. But there's a lot of mistakes that still happen, even with these things in place, because again, the ID gets lost, so on and so forth. There's lots of issues there, right? So one huge application of this is to make sure that when you're taking an infant out of a hospital, their biometric matches at the time of birth, whatever their biometric was, which is why we went as low as 6 hours after they're born. Can we actually still identify them? The answer is yes. So the idea is, okay, baby swapping is one thing. The other aspects of infant mortality, and an excellent point, by the way, is that in many countries, especially the underdeveloping countries in Africa and so on and so forth, they use or they need a way to track if a baby is properly vaccinated, because many times the parents don't go, so on and so forth. So there needs to be some way to track if a baby is vaccinated or not, if they're getting proper ration, proper healthcare, so on and so forth. That's where this concept of infant mortality comes in. This was also identified, by the way, by UNICEF. That's one of the reasons they also push for having digital identity for each and every human, regardless of their age, by 2030. That is one of their goals that they have set out a few years back, right? The idea is, again, that if we are able to track these infants as they're born, you can then track their vaccination cycle schedules, immunization, so on and so forth. And that ideally and hopefully should help reduce a lot of the deaths that may not have happened if we knew which baby is going where and who they are and so on and so forth. Hopefully that answers some of the items. The other aspect is, of course, you have a ID card that the hospital gives you, a birth certificate, so on and so forth. These documents are sometimes forged or lost at the end of the day. So now if the ID document is lost, what do you do? Who is this baby? You have no clue, right? So that's another aspect where, these kinds of fingerprinting for infants is extremely important when, as soon as they're, let's say, born.
Yeah, okay, thank you, sir.
Mm-hmm.
And Dr. Dev, there is another
Yes.
question in the chat box from Dr. Bhargavi Balla. Wants to know that how did you combine handcrafted features while using CNN in your work?
Oh, very good question. Yeah, so there are many ways to fuse these two informations. So let me talk at a very high level here. Actually, this image was really good. Okay, so at a high level, there are many ways to combine information, as you may be aware or not. But a deep learning, usually deep learning networks, especially convolutional neural nets, have these bunch of filters that go through. So you first pass in an image to the AI model here. You have, let's say, a few convolutional layers, and then at the end, you have a fully connected layer that gets you the final feature that describes this human or biometric, right? So first thing is, let's say at each and every level, you can have some sort of fusion of information that you can provide. The first most basic level is the image level, right? So in here, there are so many different ways you can fuse information. So for instance, if you remember the iris work, we were trying to fuse two different images completely, right? So one was an unwrapped iris image, and one was the raw image of the eye itself. So again, how do you fuse two different images? There are many, many techniques you can use. We did something very simple, which is to take the raw image and then take the unwrapped iris, simply concatenate or like fuse those two images together. Top is, let's say, raw, below is the unwrapped. So this kind of approach is, let's call this image-based fusion. This kind of approach helps in situations where you want to sort of enforce certain features that are already present in the image. And maybe that new image that you have is slightly different kind of information from the original raw image that the CNN may or may not have taken from the original image itself. So that's where the iris part helps a lot, because in the unwrapping process, we are showing it another view rather than a circular band view of the iris itself. So we're sort of, making it a kind of more attentive towards these iris features as an extra point, right? And if it wants to ignore, it can. It's a very cheap operation at the end of the day. Just take that image, stack them together, pass it through the model. The other approach in fingerprint, we tried a few more, which is now going deeper into the stack. So instead of the image part, the most naive way would be to take two different CNNs completely and have two different kinds of images coming from two different domains, right? So one is you take the raw fingerprint image, pass it through one model that only knows how to extract features from a raw fingerprint. The second CNN model that you can train has only the minutiae information. And so it just learns how to extract the patterns from like all these minutiae points. It has no context of the fingerprint shape, the ridges, valleys, nothing like that. So then what happens is you pass both these images through these two different convolutional neural nets. You get two different representations, features, templates, whatever you want to call them. You can then stack these two templates together, simply concatenate them. and that is your final feature at the end of the day. Again, in this case, how this can help is, of course, now you have, let's say, two dedicated AI workers that are looking into two vastly different feature sets. So it's a very powerful technique, even though it's a naive, approach. It's very, very powerful in terms of modeling. But there are many issues that you will get there, as always. The largest issue is that now you're having to pass through two different large models and two different images. So the time to infer, or the, let's say, matching time, template creation time, all these times now go up. And finally, your feature itself is now either doubled or much larger than one model's feature representation, right? So the final approach that we took was to basically see which region in the whole convolutional neural net pipeline we can branch off. So it's like you start off with one CNN. So you have a few convolutional layers, early layers. Then you branch it off to, a few more convolution layers that are now just focused on minutia. And then you branch off another branch that just focuses on the rest of the images. And then the final two features you try to concatenate. So it's like the hybrid of these two approaches. And so that's finally what we came up with that worked, sort of like firstly much better than having minutia or texture alone, but not as good as having two different models and combining them, of course. But this is a compromise that we took. So again, very, very good question. I hope that answered.
Dr. Deb, there are a few more questions in
Few
the
more,
chat
yeah.
box.
I just
One
saw
is
them.
from Dr. Nitin Soni. He wants to add face data in IoT device for face recognition digital footprint. So I
Okay.
think he's looking for some inputs from you.
Mhm.
And then,
So,
yeah, there's another question also.
okay. So, yes. So I wanted to ask, actually, I'm a bit unclear on the wording here, perhaps. Dr. Soni, if you can clarify a little bit for me on the digital footprint part. So if it's the concept of can we use IoT devices like a Raspberry Pi? If I got your question right, is it something like you want to run a face recognition system on this Raspberry Pi, and how we should go about doing that? How do we optimize these huge models and make it fit? Or it's something else? I just wanted to check with you in the meantime. So, and so while we reply, maybe I can take the next question, which is, using GAN model to generate future fingerprints of an infant. Could you tell few applications where this problem statement can be used? Yeah, that's really interesting. So again, whenever you look into synthesis of biometrics, the number one problem statement that you have is collecting data. So again, imagine going to each health clinic, asking their all infants' parents, hey, can I collect fingerprint data to train a fingerprint recognition system? It's very, very difficult to do, right? So again, having something like a GAN model, as you said, to synthesize fingerprints of an infant can help. Now, if there's another aspect, which is which I already kind of alluded to earlier, which is you can take an infant's fingerprint and also try to age it. So you progress the age, how it would look like after 5 years or 10 years. And something we actually do for face, even internally all the time, right? I'll show why that's really cool. But yeah, you can actually age progress a fingerprint from an infant to perhaps improve performance more, because then you could potentially compare two different, you're comparing two fingerprints of the same person, which one was an infant and one was the person maybe today, right? So then you can match these two in a much more effective way. This is also helpful, by the way, if you are looking into identifying missing children. That's another problem I tackled using face primarily, but for fingerprints, it can be also very, very useful to have a GAN model, as you suggested. So what you could do is when baby, when you have a newborn, you enroll them immediately, and then you can age progress. So let's say he was born in 2012, it's 2024 now, 12, 13 years later, how would their fingerprint look like? So if they ever go through any system where their fingerprint is collected, maybe that would match a lot better than their infant fingerprint versus today's. So that's another aspect where generative models is very, very useful. So hopefully that answers your question. Yeah.
Yeah, I think we can proceed now, Dr. Deep.
Okay, thank you, Dr. Preeti. So let's talk now about face. One of the most interesting biometrics for sure. Again, the challenges are quite similar to fingerprint and iris when it comes to face as well. We had a lot of handcrafted features in early years where people were using things like appearance-based models, or you had things like you really handcraft the distance between two eyes, distance from the bridge of the nose to one of the eyes, things like that, and you notate these distances. And again, whenever you have a future face coming in, you try to see how similar these distances are to say if it's divine or not. Of course, straight away, there's going to be tons of problems, right? First obvious problem is, let's say I turn my face like as a profile. How do you even measure these things where one of my eye is not even visible? Then you have issues like these handcrafted features are just us humans deciding is how we are identifying a person from another person. But there might be a lot of other features we are completely missing out, like some textures of the skin, some marks, some scars, so on and so forth. There's so much information that's present in one face image that we're just completely discarding. And so that's another aspect where and this was one of the first biometrics where deep learning was proposed by Facebook, actually. It's called DeepFace, and it was released in 2014. At the time, there was not much attention paid to using neural networks and deep learning in the field of biometrics, but with our push in fingerprints, which was one of the most classic papers even today, people started getting interested in face as well, and then they revisited this paper, and then this paper also blew up. So there was like this really golden time where deep learning was primarily being used a lot in the object recognition domain, but in biometrics it was very untouched. Even today, especially in iris, there's very few vendors and other companies or even research labs that work with convolutional neural nets, and also same with fingerprints. Face, however, there has been so much research already done with deep learning, primarily because it was one of the first biometrics to have been proposed to use deep learning there, as well as you have a ton of data available on the internet that you can scrape, download. Also in the public domain, there's a lot of faces that are available. So because of the sheer size of the data, there has been a lot of very, very good models that have come up the past few years. But at the same time, actually, the face recognition problem itself is actually a lot harder than something like a fingerprint matching in terms of accuracy, because of all the variations you can have. So you can have variations in lighting, the way you're reflecting light can change from one image to another. If you're outside versus inside, things change. There are tons of challenges, and we can go over a few of them. Most of them would be very much obvious. And I'll talk a little bit about how we have solved a few of these challenges and some that are still pending and we're still working every day on at Lens. So one of the largest challenges for face, unlike fingerprint and iris, is the problem of aging. So since we have so many different, let's say, features on your face, but also we have the largest organ, which is the skin itself, that ages very rapidly, as we know. So you have wrinkles, you have other kinds of marks that appear. So all these distinguishing features that make you today can vastly change 10 years from today. And this is very normal. We all know this. We all see this all the time, where someone ages and you're like, oh, I almost did not recognize you, right? So this is a very, very common thing that happens, and it's a very natural process. But we need a way to tackle it. One of the ways you do this is something I already briefly talked about, which is what if you sort of age progress in this case, let's say a child's face, and try to normalize the ages. So the idea would be you learn a generative AI model again. So a little bit more technical I can go into on this because it is a very interesting concept. So the idea is, let's say if you have something like an autoencoder where you take a person's image, you encode it into a set of features, and then you decode the same image back, right? In theory, if you can imagine, the feature space itself is static, right? This will never change once the model is trained. So if it never changes, and there's no theoretical limit to what the image could be, that means any image in the world that has a face in it, we should be able to encode in this feature space. In other words, at a higher level, you take my face from, let's say, 10 years back to today, there has to be a set of features that hasn't changed for a deep learning model. So in theory, there must exist some point in this feature space where there is Debian at 10 years of age and Debian at 24 and 30 and so on and so forth. So now if we have these points in this feature space, can we learn how to transform from the 10-year-old Debian's features to 24-year-old? What is that transformation function in this very small feature space that we designed? And so that's what we're trying to showcase here. This is one of the techniques we came up with, which is you learn sort of to walk in this feature space, and then you see what are these features that change is one interesting aspect. But more importantly, you can take any face recognition system that's out there, any deep learning model, get its feature, and then get its feature for the same person after a few years. Again, find that feature representation and then learn this transformation function. So you don't touch the face recognition system at all. You leave it as is, just extract these features out and just learn how to walk in this feature space. If you can do that, then okay, these sets of features are stable, these are not. And more interestingly, you can train a transformation function that takes these two ages into factor. So the age of image 1 and the age of image 2. And then you can normalize these two things and say, I want them to be matched at the same age, be it the younger age, be it the older age. This is extremely important, and the performance was incredible. If you go to this paper, you'll see the results of it. But doing it this way, now you can enable a lot of other applications. As I mentioned earlier, you have things like missing children. So a child gets lost. Very, very likely you still might have an image of the child just before they went missing, compared to, let's say, an iris and fingerprint, of course, right? So you might have a photograph of that child when they went missing. You then age progress it every single year, let's say, like they went missing in 2012, how would they look like in 2013, 2014, so on and so forth, until they're today, and then you still try to match to, let's say, Aadhaar database or something, and then see if you get a hit. So that would be the approach. The thing that's different here, though, is that we're not necessarily focused on age progressing the image itself. So it's less to do with visually how amazing this person matches the current person today. It's more of, for a face recognition system, how do we age the feature itself to make sure that that matches the feature from that person today? So that's the interesting concept here. Why it's interesting is that there has been a lot of work, making you look older, look younger. What we find is that that has very, very little, if not at all, to do with how a face is encoded with a face recognition system. And these features that it's looking at, they may or may not age the same way a photo ages, for example. That's the best I could describe it. But this was a very interesting concept where we are actually aging the feature of the person. And this feature is from a CNN model right? So, and again, the results were very good compared to, let's say you take any off the shelf, those Snapchat filters or anything you want to use to age your image itself, right? So this was all about aging. And so, of course, it's still a work in progress, but we've made huge strides, let's say, in lowering the gap between, having really good face recognition performance when the age difference between two images is a lot. So that's still an ongoing challenge, but we have reduced the gap. The next item, of course, is occlusion, and especially with COVID, this has been a massive challenge for all face recognition systems that are there, which is, of course, if you're wearing a face mask or some part of your face is occluded. I shouldn't say some, a large part. These deep learning networks are very good at it, but if a large chunk of your face is missing, how do you still identify the person? There are many techniques to tackle this. One of the ways we do it is by trying to hallucinate or in paint. So you detect these masks first, and then you try to generate how the rest of the face would have looked like, for example, from any other part of the face that you have information for. So you get one image. And then what you do is when you're matching it to a database, you take that same like face mask or whatever covering that you had, you make that apply to each person in the database itself. So you take that mask, paste it on top of all the images in the database or gallery that you have, and then you in-paint all of them. And so then you see which is the closest match. Because it's going to hallucinate or in-paint there as well. And then ideally the in-painting mechanism itself is similar for the same person. That is one way you can tackle this that we've tried. The other approach is, of course, the more simpler ways, you just reject if you see there's a face mask, and then you let the person know that can you take off your face covering, so on and so forth. But then again, that's a lot more invasive in places where you just want someone to walk through, and then you just want to know who just entered the gate without asking a lot of questions and back and forth. So something like a generative AI model is where I see this field going more, and we should be able to tackle this and again lower the barrier significantly here. And also, a lot of people do wonder if eyeglasses matter. Mostly no, just because of the sheer amount of data that we train with. So in-house, we do something like 300 million images or so that we train our face recognition systems with. So there's a lot of data that we're talking about and these are real data, right? So no one is posing for the camera or anything. This is all in the wild. So most people will have images with glasses on, sunglasses on, so on and so forth. So these models tend to ignore a lot of these features when someone is wearing glasses, let's say. So that's about the face occlusion part. Then you have this problem, which is you do find a lot of doppelgangers. For example, here there's Obama, and then there's someone else that resembles Obama quite significantly. And so how do you tackle this? So this, I'm putting it here just as an interesting case study in general for face recognition, but in our experience thus far, most recent cutting edge face recognition systems do not get affected by this. So for example, this our matcher completely rejects as two different people, even though to us they seem a little bit similar. So that again now shows what I was telling you earlier about the aging of the features versus image. Images are very deceptive, and the way the features that we look at is also very deceptive compared to what these convolutional neural nets look at. They look at much deeper level combinations of different pixel information at the end of the day. So again, doppelgangers is not a big issue in general today, but it used to be a huge problem for the earlier traditional based face recognition systems. Similarly with quadruplets, and you can keep going. Twins, so on and so forth. Again, there are still enough distinguishing marks from our experience that we have not had this issue. In fact, NIST also evaluates, when they're evaluating your face recognition system, they also evaluate your performance on quadruplets, triplets, twins, so on and so forth, identical ones. So far, there hasn't been a big problem as the earlier models used to have. So, sorry, was there a question?
Yes, Parul.
Yeah, okay.
Yes, ma'am. Sir, I just wanted to ask, like, when you did the your experiment with this facial recognition system, so are there any facial features that does not change even after some plastic surgery and or any other surgery on face?
Yeah, so there is a maxillofacial surgery that people do. So this is basically altering the jaw side of your face. This one affects significantly the current face recognition systems, at least that we are aware of. But of course, let's say if you're doing a full face, alteration, that would definitely throw the matcher off. There is no way to recover or do the matching at that point. You'll have to go and re-enroll yourself. So there is also a push, by the way. So when people are getting these things done, there is a push in policy so that you have to necessarily go and re-enroll yourself to a Aadhaar or any other social identity program. So there is no way to tackle that problem as of today, let's say. And similarly for partial face, the largest thing that affects, as I mentioned, is your jaw surgeries. So maxillofacial surgeries do affect quite a bit. Rest of anything, it doesn't affect much. So for example, we've done a lot of experiments with nose alteration before. So those things do not affect in any significant way. Also, let's say I personally tried this quite a few times, where I use these contact lenses, for example, change my eye color. None of those really affect the matching performance. The other thing I tried, so I have a cut on my eyebrow here. So I tried to put like fake eyebrows to fill that whole thing up. So this feature is completely gone. Even then, of course, the similarity goes down, but it's not significant enough to say that it's not divine anymore. So the largest problem happens, of course, is you alter the lower part of your jaw completely, or you're doing a full face surgery. That's where it's completely insolvable almost today. The performance is very, very bad. So I hope that answers. Yeah.
Yeah, okay. And one more thing, for the iris features, so like wearing contact lenses does not affect the iris recognition system.
Oh yeah, good question. Yeah, it actually does. It does affect the performance, especially if you're looking at the unwrapped one, because your color and everything is off now. So it does affect quite significantly. However, if you're using something like a convolutional neural net, you are much more protected in terms of performance. It still drops, but it's not that as much as, let's say, if you're doing a traditional, as I told you, right? You unwrap the iris and just look at very simple SIFT, Gabor, any sort of traditional filters. They will be very much affected by contact lenses. So, but at the same time, there are many applications where this is not a big problem, because there are some government organizations government institutions where you cannot wear a contact lens, and the iris scanner actually detects that. And alerts, so you have to take them off before you go and authenticate. So sometimes you have situations where iris is not very commonly deployed, let's say at the borders, but you have situations where you have like like law enforcement, for example. They collect a lot of your iris, so they will make sure that you remove your contact lens so that there's no problem doing the matching part. But also at the same time, they're using a lot of these traditional iris matchers, not these convolutional neural network ones, which is again what at Lens we're trying to push towards. That we should push a lot of people towards CNN-based iris matchers. So that would be a very good way to identify someone.
But is there okay, yeah. Then it's okay. Thank you.
Mhm. Okay. So I'm going to continue, unless if you have any questions, please feel free to raise your hand. So the other aspect is scars, marks, and tattoos. Sometimes the having a scar makes you unique or a mark or any tattoo, of course, it makes you unique. But the problem is there could be another person that has a similar tattoo. So now you're artificially becoming similar to that person, to some of these convolutional neural nets. Because again, we're not looking at it from handcrafted features. We're looking at it from, you throw a bunch of data to essentially a computer at the end of the day who's just learning whatever it can to improve the accuracy. So that would mean that if you have a tattoo on your face, it would be a very, very discriminative feature, that it's going to think that this tattoo makes the Bayan who he is, which again, to a certain degree is very true, unless someone else has a tattoo that's very, very similar, location as well as the style of it. So one of the big things that we work on also at Tech5 and at Lens is the scars, marks, and tattoo detection. It's extremely important to do that, but also use these as an identifying feature. So let's say you can give a description of the tattoo, and then it can go to the database and pull up whose tattoo looks most similar to this description. So there are some advantages to this, but it does affect face recognition performance. It might, let's say, if someone else has a very similar tattoo to you on your face. So that's, again, a challenge. Face spoofs, this has been a big part of my dissertation during my PhD that I worked on, which was essentially trying to do two things. One is to see how I can break a face recognition system that's currently deployed everywhere worldwide, the best models that I could get my hands on. In fact, one of those models was a model that was deployed at the border at that time. Of course, they have changed it now, but at that time, it was literally the face recognition system that was running the US visit border. I was able to break it in a few ways. So one of the ways is, of course, you can have something called physical attacks. So what I found is you can break it in many, many ways, right? So you can have things like a mask, which you're trying to impersonate someone else. So Obama, Donald Trump, whoever, you just take their mask, you can either print it on a piece of paper, show it in front of the camera. You can play, some celebrity's video on your phone, show the phone in front of the camera. That's called a replay attack. Then you can, craft these very high resolution silicone masks that, a lot of actors wear in Hollywood or Bollywood. So I was able to get a few of these masks hands on. And then saw if you can break that. That's also very easy to break these face recognition systems that way. And then there's some other ways, like you have a lot of makeup you can do to impersonate someone. You see those YouTube tutorials. So I downloaded a bunch of those videos to see, let's say if someone's trying to, make themselves look like a certain celebrity, I take the celebrity's photo and try to match how much does that affect. So there is a lot of such attacks you can do to face recognition systems. One of my first studies was to see how much it affects. And then the next is, so that's a problem, let's say. The whole paper talks about the problem. And then the next big paper was on how to solve it. And so we came up with this approach where we look at so traditional methods to detect, let's say, a printed paper or a replay attack was to look at the entire image and see if there are certain features that are different from a live face video or an image. But instead, what we figured is that if you look more regionally, you can start detecting a lot of different types of attacks that would be missed from earlier methods, like a paper cut. So just a portion of the face is printed, let's say, or paper glasses, or these funny eye things, so on and so forth. So the exact approach, if one of you wants to ask me, I can go, but in the interest of time, I'm going to skip over it. You can look at the paper, but it's more of making the convolutional neural net look at very regional and local features rather than the entire image at all times. So it's a combination of various different global, local, regional features that we combined to detect if a person is alive or it's a fake that's trying to attack, right? And more problematically, and this has been
Dr.
sort of
Dev,
yes.
can I just ask you one question over here when you're talking
Yes, please.
about face spoofing? So currently, apart from this, there is a lot of research going on adversarial deep learning where the face is not spoofed, but a very uh, small amount of noise is added to the face to try to fool the deep learning system. So did you try that also in the face recognition or other biometric systems as well?
Excellent question, Dr. Preeti. So the first paper that tried to spoof a face recognition system by just manipulating a few pixels, it actually was proposed by me. This is that paper. It's called App Faces. So I was one of the first people to actually try it on a face recognition system, and I was able to fool this. It's still my most cited paper. So it's a very, very big problem. And I was actually just getting to this exact point, which is these physical ones are more obvious to, let's say, you and I as humans, because we can see that you're trying to do something in the physical world that's off, right? It's not normal. These adversarial attacks that, again, as I said, I was one of the first to try it on a face recognition system. And today it's a very popular field and many researchers are working on this. I left it long time back, but my research showed essentially that you can first manipulate, and I came up with an approach, a generative AI approach on how you can make sure two things. One is, let's say you take my face image. What are the most salient or most important pixels if I just manipulate the least amount of? That will completely throw off a real face recognition system. So I use the FR system in the training of this generative AI model to know which pixels to perturb or change. So that's what Add Faces is. And if you see, I know something happened with these slides, but on the left, you will see Ming Xi, a Chinese celebrity. Her real image is on the top, and then the adversarial image is on the bottom. They are very similar, let's say, to the human eye. But the one in the bottom, we can completely not match with her gallery, where previously was matching with 78% similarity. So again, this approach, I would really, really like if some of you guys can go check out this paper, and feel free to shoot me an email on this. It's still one of my most fun work that I did. But definitely, Dr. Preeti, this problem is a deeper problem, let's say. The only reason, let's say, in the real world, people are less still worried about, especially in industry, on adversarial attacks compared to physical attacks, which was the prior slide, is that the launching this attack is very difficult, especially in a real-time setting. In a real-time setting, you can wear a mask, you can do many things and just try to go through it. But launching an adversarial attack is difficult on a few fronts. One is there are very few applications, let's say, where you have face recognition being done in a mission critical level where you just simply upload an image and there's no human to verify you. So this happens very rarely in practice. Let's say you're going through a border. It's very difficult for you. Let's say, where are you uploading an image? You have to stand in front of the camera. So it's very hard to, let's say, launch this attack, essentially. So that's why, like, a lot of people haven't focused a lot, let's say, in industry to solve this problem in particular. And one of the reasons we also are not heavily working in this field today. But at the same time, it's much more of an academic problem, which is, forget face or biometrics for a second. This problem occurs because of these convolutional neural nets, because we're not understanding what are these features that they're using to improve their accuracies. If we don't know what these features are, we don't know if they're aligned with how we as humans are identifying different objects or different people. That is where the entire problem of adversarial attacks lie. What it's trying to show us is that computers, especially these AI models, are not smart enough yet to they're kind of like an arbitrary function where you're rewarding them just with one cost function, which is just make sure the performance, the whole performance of the data set is as good as possible. Just learn anything you can from these images to make these, reduce the risk of making an error anywhere, right? I believe that having this kind of a loss function alone is not enough to train these convolutional neural nets. You'll always have problems like adversarial attacks because it will be combining the randomest and the most arbitrary features together. And then if you change just those features, for us, nothing changes because we're not using those same features to identify you. But for the face recognition system, those features were very important, for example. So there's a misalignment, let's say, of human interpretation as well as the convolutional neural nets interpretation. And that is why we try our level best to make these models as explainable as possible. We try to backpropagate and make heat maps on which areas of the face the model is attending to, and generating all these attention masks, so on and so forth, to make sure we have a vague, if not more accurate, idea of what these features are. So this was a very interesting, let's say, conversation on adversarial attacks. And so I'm not sure, Dr. Preeti, if you have time, if you're running out of time, but I can very quickly cover one of our flagship products as well, if someone's interested.
Yes, I think the participants are really enjoying this session a lot, and we would love to have it continue. But I see Professor Subramaniam, our next speaker, has already joined in.
Okay.
So but we can, I think you can we can go through it in a fast paced kind of a manner.
Okay. Thank you also, Dr. Subramanian. Sorry, I'm just going to take a few minutes, just quickly cover this part. Appreciate it. So Lens View is one of our flagship products in our company. The idea is, so far we've been talking about identity and security in the digital identity sense. The next natural step, at least for me, was to take this at the next level, which is the surveillance side of things, which is, you have a lot of these CCTV cameras, but even today, even after we have so much advancement with ChatGPT, large language models, diffusion models, so on and so forth, even today, the actual cameras that are deployed in the real world, they're not doing anything that I would consider as a smart feature at the end of the day. So let's say a child drowns in a swimming pool, she's drowning, it's not alerting anything, it has no idea, it's just recording a video at the end of the day, right? Or someone's held at a gunpoint, no one is alerted at the end of the day. So all these surveillance systems that are existing as of today, they exist only as an evidentiary purpose, a judiciary purpose. So you just have evidences of some incident that took place. So you can go back and view the feed, see what happened, so on and so forth, after the fact. The idea with Lens View is that there should not be an after the fact. If we can detect and alert authorities in time, we could literally be saving lives, or many, many other things can come into play there. And for that, there are three major aspects that any video surveillance software should account for. One is the latency of these video feeds should be as minimal as possible. What that means is, if you look at existing, video management systems that exist today, most of them work on a protocol where you have a surveillance camera here, and if I view it in, let's say, the US or any other country, there's going to be a big lag. So let's say it's running at a certain time here, X, and then in US I would be seeing that feed of a time that's much earlier than actual X. So there's a big lag that you get, so it's lagging behind. So that's one problem we have to solve. Next problem is that, let's say everything is real time, wherever you're in the world, there's as minimal latency as possible. On that, you're running all these AI alerting systems, right? These analytics. So if someone is drowning, if there's a weapon or anything like that, you're able to detect them. The next problem is, are you able to detect them in a timely fashion, where you're able to then go and alert the authority immediately? That's the second problem, which is the latency of the AI inference itself. And then the last problem is, of course, making it extremely robust in the sense that it can work by itself. You don't need a human. Let it just do its thing, and you'll get WhatsApp messages or SMS, email, so on and so forth, whenever there's something that happens in the scene. So in summary, there are close to 40 or 50 AI models that we work on today, and these are actual models. Then you have other kinds of engineering that we do on top of that. where we build the entire software. We also have the AI parts in it, like you can count how many people are present in any given scene, even across different cameras. So we can know that, so it's not like per camera you have 12, 13, so on and so forth. Even if you have 12 cameras looking at the same scene, you will get that unique count of people in that entire area. Then you have line crossing. So if someone's crossing some sort of perimeter, you will get alerted. And then you have intrusion. If someone is, there's in a location where they're unauthorized to be, or there's some suspicious activity that they're doing, it alerts the authorities. And then we also do a lot of retail level analytics. So something like heat mapping. So you know how many customers are there in your store. Not only that, but which area of the store are they mostly hovering around. So the density. Then you can do fire and smoke. We do fire and smoke detection, as well as we detect if the security guard is there on his post or not, so on and so forth. There's a ton of other features, and I'd love to talk more on it. But again, in the interest of time, I'd like to thank all of you for listening. Really appreciate it and having me talk. Thank you. And again, any quick questions I can take. Yeah.
Okay. Any questions from any participant? It has been a very interesting talk, Dr. Devayan, and the way you have shown us the challenges associated with different biometrics. I'm sure the participants would have benefited from that knowledge and will be using that in their future research. And I think we need to arrange one more session with you in the future to understand all the features of this new product view. So thank you for joining in once again.
Absolutely. Thank you so much, everyone.
So
Appreciate it.
there is one small query, Dr. Devan.
Yes.
The thing is that initially you talked about some lightweight models, and what are the lightweight models are right now it is available, uh, which can be like use some sort of segmentation or like recognition task with very lesser resources.
Yeah, I can tell you like the off-the-shelf models do really well on the segmentation side. Like you have EdgeSAM, for example, it works really, really fast, right? But mostly all of them rely on these depth-wise convolution operations. And then you have models like GhostNet for face. I think they do it for general object recognition as well, EfficientNet, so on and so forth. So there's quite a few available, but in my experience, anything with a very lightweight transformer model is obviously beating the traditional CNN ones.
Yes.
Yeah.
Okay.
And then more
Okay.
importantly than that, I would also really emphasize that you should also look into not just the inferencing part, but which framework you're deploying on. So a few I can just mention without violating any NDAs, but you have like OpenVINO, NCNN, MNN, lot of different, very, let's say, optimized operations at the lower tensor level. So the framework that you finally run is actually even more important than the model itself in many cases.
Yes, absolutely.
Yeah.
Thank you. Thank you,
Thank you, sir.
Dr.
Yeah.
Devan. Thank you.
Thank you, Dr. Dev. Thank you for joining us today.
Thank you, ma'am.
Um, we welcome Professor A.V. Subramaniam from IIIT Delhi. He will be taking our next session. Dr. Nikunj, please take over the session.
Yes. Okay. Okay, ma'am. Okay, so
Uh, yeah, hi, Dr. Nikunj.
hello, sir.
Yeah, hi. Should I share my
Good
screen?
evening, Dr. Subramaniam.
Hi, Dr. Singh.
Good
Yeah,
evening.
Yeah. Okay. Good evening, everyone. It is my pleasure to welcome you all to session 8 of our ATAL FDP. We are delighted to have with us Dr. A.V. Subramaniam, Associate Professor, IIIT Delhi, expert in AI and deep learning. In this session, Dr. Subramaniam will speak about advancing sequence models from RNNs to attention, Professor A.V. Subramaniam completed his PhD at Nanyang Technological University, Singapore, and undergraduate studies at Indian School of Mines University, Dhanbad, India. He works in the area of multimedia and vision, image processing, and machine learning at IIIT Delhi. In particular, he is working on problems in fine-grained object recognition with applications to object re-identification and visual tracking, adversarial attacks, and cross-model recognition. He is the recipient of Ali Career Research Award, Department of Science and Technologies. His research group, Visual Conception Group, maintains an active collaboration with leading institutions like NUS Singapore, QUT Australia, NI Japan, and UIT Norway. We are grateful to have you here, sir, and look forward for an enriching session. So let us warmly welcome Dr. A.V. Subramanian to begin the talk. So it's over to you, sir. You can proceed with your presentation. Yes. Sir, can you please unmute yourself? Please unmute yourself. Okay. Okay.
And
Just
yeah, I hope
yes, sir. You are audible now,
okay.
loud and clear. Yes,
I will make this full screen, and I hope the slides are also visible.
yes, sir. Yes, sir. Visible.
Yeah, yeah. So thanks, Dr. Nikunj, for the introduction.
Thank you, sir. It's my pleasure, sir.
Okay, make this full screen. Yeah. Okay. So I would just add that I mean, the other details of our visual conception group can be obtained in this website, vcg.iiitd.edu.in. Uh, so I will speak about the building blocks like attention mechanism. Um, so as the talk says that we are moving from RNN to the transformer models, and where the fundamental blocks are the um, attention mechanism. So if you see the transition, CNNs, like last decade, CNNs were very heavily researched upon, but roughly come this decade, 2020, 2021, uh, there were models, especially in vision, there were models which showed that with attention mechanism, they can beat CNNs. Attention was already popular in NLP much before vision, around 2017. So this attention thing is borrowed from this NLP community, and we'll see how we transition from CNNs to the transformers more from the vision side. I primarily work on multimedia and vision, and I mean, so that includes language as well. I would like to upfront give credits to Professor Ali Ghodsi, Professor Justin Johnson, very well respected researchers in the community. And if you're interested, please go through their YouTube lectures. Professor Justin Johnson gives a very good overview of basically very advanced research, very recent research. And Professor Ghodsi attacks things from the mathematical foundation. So let me begin with the content. Um, so the precursor to attention basically, it was supposed to handle text first, and then it came to vision. So in principle, it can handle any time series signal. So the models that were popular for handling time series signals, one of the first models were called recurrent neural networks. That came up in quite early in the game, around 86, and on the same time when backpropagation was introduced. And these models are capable of handling variable length inputs, because time series, I mean, the signal could be of very different length. Take an example of audio, speech, ECG, any physiological signal. They could vary in length. And even a precursor to RNN is like, I mean, they were borrowed from this classical system of dynamical system. So here we, okay, so here let's say we have, say at a particular time step, we have a certain state, and we have correspondingly a previous state, and we have some parameters. Usually in case of neural network, these are learned, but otherwise they may be empirically tuned, or if they are known otherwise, I mean, either ways is fine. So this previous state is acted upon by this parameter, this function f theta, and we get a current state. And current state is again worked upon by the same set of parameters, f theta, and we get a new state. So this set of parameters is same across all the time steps. They have to be, otherwise the model won't generalize if we go on introducing new parameters. So at any given state, it's acted upon by f theta, and we get to new state. And now consider introducing an external signal, say xt. Okay, so my pen is probably, yeah. Okay. Say we introduce this external signal xt. Uh, it's still the classical dynamical system, but with this external signal xt. So previously our equation would have read st is a function of st minus 1, where the function is f theta. And now we have another parameter, the signal xt. At any time step t, I have introduced a signal xt. So at every time step, we are getting some observation. So that is my signal xt at that particular time step. So now my current state st is a function of previous state st minus 1 xt, and acted upon with this parameters f theta, and it gives me a new state st plus. Uh, it gives me this state, and again this state will be acted upon with these parameters along with this particular signal, and I get this particular state. So all in all, any particular state is like a summary of the entire past sequence. So for example, if I look at st, then it could be a summary of xt, xt minus 1, so on and so forth. So it's summarizing the entire signal for me. So just in case, if I don't know how the Q&A goes, but if you have a query, maybe I'm not sure if unmuting is allowed, but otherwise maybe chat box or other things are also fine. Okay. Um, so using this classical form of dynamical system, um, we have a formulation of recurrent neural networks. Again, in the same setup, we have some state, we have some input signal. So if I look at this particular state, how would I obtain? So I have this state again acted with this parameter w. So I have, say, w parameters which act upon this previous hidden state st minus 1, and I have a signal at the current time step. U are again the parameters, so u parameters act upon xt, and we would have a bias. So this is just like our simple linear layer. I mean, you can think that I have a vector input passes through a linear layer with some bias. So that could be represented as wx plus b, x being the input, w being the weight matrix for a fully connected layer. And it gives an output AT, and then we have an activation. Could be any other activation. Tan H is given over here. That gives me a current state ST. So we used previous state, current time signal, these weights W and U, and bias and Tan H activation to obtain the current state. And if you want some specific output at this particular node, then whatever this state is, it would be a vector. It would be a vector. It can again pass through another linear layer, which is parameterized by this matrix V and some bias C. Again, just like passing through a linear layer, and pass through another activation, say softmax, and we get we get the probabilities. And if we want, we could apply a cross entropy loss onto that, or I mean, whatever accordingly, whatever is the task, I could change this activation or change the loss function. And this would be unrolled in time steps. So again, you see that W and U, they are shared across different time steps. So for ST plus one, we'll have WST plus UXT plus one plus B, and again at time H, and whatever it comes out, then I will have VST plus one plus C.
Uh,
Excuse me,
excuse me,
Professor Subramaniam.
sir.
Yeah.
I think the slides are not changing. Are you changing the slides? Because we are not able to see the new slide.
Oh, is it? Okay. I am.
Yes.
The title of this slide is recurrent neural networks. So this slide is
So
It
we are
is it
currently,
is
it's showing
dynamics.
dynamic systems only.
dynamic systems. Okay. Is this a slide that is appearing? I mean, dynamic systems. Now consider a dynamic system with an external signal X. Is this the slide that is showing up?
No, the
Uh,
classical form of dynamical system. This is the slide.
Oh, this is a slide. Okay. Classical form of dynamical system. ST is F theta ST
Yes,
minus one, right?
yes, yes, yes.
Now I'm going to move to the next slide. Um, isn't it visible? Like ST equal to F theta ST minus 1 comma XT.
Yes.
Is it visible?
Not yet.
Not yet.
No.
Oh, okay. Okay. So maybe the full screen. Okay. Okay. Please let me know if it is moving now.
Yeah,
Um,
now, yeah,
Yes,
it
it
is
is.
moving now. Yeah.
moving, right? Okay. I
Yeah.
guess the problem is with the full screen.
Can you try once again? Maybe we can check once again.
Okay. Yeah. Let me go back to the full screen mode.
With the slideshow.
Okay, just 1 second. I'm going back to the full screen mode.
Because you're just
Yeah.
sharing a window and not the entire screen.
Huh,
Could
yeah,
be
yeah, yeah.
because
Oh,
of that
okay,
also.
okay. There is that the okay. Let me share the entire screen. Right, that could be a cause of this thing. Okay. So let me stop presenting. I will, yeah, entire screen. Um, okay, entire screen is it? Okay. So I have done the entire screen thing, and let me move on to the full screen. Okay, please let me know if the slides are moving.
The screen has not been shared.
Okay. I see. I need to click this guy. Okay, it should have now. It should have been shared, right?
Yes, yes, it's coming now.
Yeah. Okay. Yeah. Now it should be moving. Right.
Yes, yes, yes.
Yeah.
Thank you.
Right. Okay. Yeah. Okay. Yeah. Thanks for highlighting that. Yeah. So I was at this slide, recurrent neural networks. Uh, yeah. Uh, I hope at least I mean you get a notion of this. Okay, but and these recurrent neural networks, they were trained using the classical backpropagation through time (BPTT) algorithm. Now, why did we move from RNN to some other networks? Primarily because RNNs they had I mean they since it's unrolled to many time steps, so the gradients have to flow through that many time steps, and that would mean that gradients may either explode or may vanish. Either of these things could happen, and in both the cases, the network won't train. So that was the primary reason. I mean, one of the primary reasons. The other reason is that it's sequential, so we cannot parallelize it. For any time step t, I have to depend on t minus one, and t minus one would depend on t minus two. So I have to process it in a sequence. It cannot be parallelized. So that was the other cause of concern. Whereas if you see all this modern DL algorithms, they are heavily parallelized. I mean, they use GPU, which in turn parallelizes things. So RNNs couldn't, they were not that GPU friendly. A successor of RNN was LSTM, popularized by Schmid-Huber. Uh, and the sequence followed. So that was the 90s decade, and there were a few other advancements like GRU until about mid of 2010s. That's where since LSTM, RNNs died down, and once LSTMs kicked in, once LSTMs died down, the attention part kicked in. So that was the progress: RNN, LSTM, and RNN attention. Okay, so let me show this illustration. So let's say if we have um, one particular input, for instance, in case of an image classification thing, we have one input and outcomes one output, which could be a class. We could, on the other hand, we could have one to many. So an image is the input, but a caption is the output. So there could be an image, and we want to have a caption like a cat is lying on the ground. So again, for the output part, it's like a sequence. A cat is lying on the ground, a sequence of words. So again, LSTMs or those things could be used. Income a video, there could be video frame, again a time series, and outcome a video classification, could be an action recognition. Income a sequence, like an English sentence, outcomes the translation of this English sentence to perhaps Hindi or some other language. This is many to many. And another many to many is incomes, say video frames, and outcomes classification for each particular frame. So there are all these various cases where time series is involved, and we have to give a decision based on such time series signals. So one of the popular papers in this domain is sequence to sequence for translation, say from English to French. And this was by Ilya Sutskever, who is associated with OpenAI. So there is an encoder, which is again could be a RNN or could be LSTM. The figure is just a representative of the previous figures. These H0, H1, H2, they all represent the hidden states. FW represents the parameters, and these X's, they represent the signal at different time steps. So so ultimately we have one particular hidden state which is supposed to encode all the past. Like in the form of dynamical system, we said that a particular state ST, it summarizes all the previous states. So in the same form, this final state HT is like encoding all of these signals, X1, X2, X3. So it has a notion of this X2, X1, X2, X3. And this being a sequence to sequence, that is, income a sequence, outcomes a sequence. So for example, in comes an English sentence, out comes a French sentence. So it goes through. Again a set of parameters which act upon HT, and it gives some hidden state and an output y1. Again, this could be, say, the first translated word. Then this y1 is now the input to the next. H1 is the input, y1 is the input. Again, there will be parameters which will act upon this particular input and this hidden state H1. And again, we get a second hidden state, and which can produce an output y2. So this could be a second translated word, so on and so forth. It will continue till the stop, till it has translated the complete sentence. So it's following like this hidden state it produces the first word, and this hidden state produces the next word, and so on, so forth. So let's take this example that we have a sentence like we are eating bread, and they have respective hidden states like H1, H2, H3, H4. So H4 would be the final thing that would go on to the decoder. So we'll call this as this whole setup as encoder, and then we'll have a decoder. So this would be just like this last hidden state, and usually we have something called a context vector, which is again coming from the same hidden state. So it's a copy of hidden state. Um, this state has 0 and C and a start token. So start token is something like, okay, the network has to begin somewhere and it has to start translating. So we have 3 inputs, again, different acted upon with different parameters. Different, when I say acted upon different parameters, means it's just passing through possibly either an MLP or just one single linear layer. They are all vectors, so just like a classical way we feed an input to a linear layer or an MLP. And it produces another hidden state, and again it can produce y1, just like in the case of RNN we said a hidden state, and again we have some parameters, say v, it acts upon this, and we would have a softmax which would give a probability uh, distribution. Strictly speaking, the classes are nothing but my vocabulary size. So if I have a vocabulary of 10, I will roughly say I will have 10 classes, and my probability, the probability vector is also of 10 elements. And whichever is the max, max probability, I will look, it corresponds to which particular word in my vocabulary. Whichever word is that, I will output that word. And now I have this first word translated. It will feed to the next state. It will become as an input to the next state, and the next state will also take this context vector C and this hidden state S1. So now I have S1 as an input, Y1 as an input, and the same C as an input. The C hasn't changed. It goes through this hidden state. It gives me this hidden state. Again, this will be acted upon with some linear layer, gives a probability distribution, softmax probability. I will pick the max, which corresponds to whichever word. I will say that is the word. So in this case, we are eating bread. It goes through this whole thing and it gives, this is a French word. I'm very poor in pronouncing this French words. And so on and so forth. Y2 will be an input to the next state. S2 is an input, same context vector goes in. S3, it gives rise to this S3 state, it gives rise to Y3 word. And that is complete translation. And finally, it produces stop. So, it stops there. So it knows that it has translated the full sentence. Pretty good. It was in Europe's 2014, one of the very good papers which achieved very good translation. Now, one of the major problems with such model was that the entire input sequence is now compressed into one single hidden state. So, say hidden state is of dimension 512 or 1024. So we have that 512 or 1024 dimensional vector, which has to encode the entire, say the entire sentence, we are eating bread. So that is one problematic thing, that is it has to encode the entire sequence. And secondly, the context vector doesn't change. It doesn't change and it remains the same. So if we have, say, a very long sequence, say t is equal to 1000, then the problem is the last hidden state would probably only remember the previous few hidden states. It may not remember the very early hidden states, the very early words. So in that sense, it will encode only the latest information. It won't encode the entire information. That is one of the problems that these networks suffer when the input sequence is very large. So one of the ways that this was handled was to use a new context vector at each step of decoder. Like in this case, so the context vector is same. So we'll use a new context vector at every step. Okay. So this came up in ICLR 2015. One of the first papers where attention was introduced. Now, how do we do this new context vector at every stage? So we are gradually moving towards the attention concept. Like till this point, the attention was not present in the form that, I mean, the way we think of attention. It may have been present in some other implicit form or otherwise, but this was the start of attention. So what attention does is so this part is the same. This part is the same as the previous model. It goes through. I have a final hidden state. Now what do? I use this hidden state and the first hidden state. Both of them pass through a linear layer. Okay, so it's like I will use say hi, say h1, and ht minus. Ht minus one is basically say in this case it's particularly this. It passed through a linear layer and it gives me a scalar. So the output of the linear layer would be a scalar. We would have an MLP which can take the entire dimension of S0 and H1 and finally give a scalar output. And so I will do the same thing here. I will do the same thing here. I will use S0, H2, pass through another, I mean, the same MLP. It passes through the same MLP. The weights are the same. It passes through the same MLP. Again, H3, S0, H4, S0. They all pass through the same MLP. MLPs, they share the weights across. And it gives a scalar value. And we put a softmax onto that so that they sum up to 1. And this is what the final scalar values we get: A11, A12, A13, A14. And finally, the context vector C is now defined in this manner. C1, the context vector for the first step of the decoder, would be obtained as H1 times A11, H2 times A12, H3 times A13, H4 times A14, add all of them. This is a scalar, this is a vector, so scalar times vector would be vector, and all the vectors are of same dimension, so we get one single vector. And Y0, it's like the network is told that you have to start translating, and we get this translation. So say for the first word is like SMU, and it's corresponding to VR. So that means that the network has to focus more at this place because it is starting the translation. It has to focus more at this place. So hopefully A11, A12, that is these, the network has to pay more focus or more attention to these hidden states H1 and H2. So A11, A12 are large, A13, A14 are small. And all of this are trainable. It's not it's not empirically tuned. So all of these are trainable. They're not hyperparameters. They are parameters which are learnable. So that was the first step. We used the encoded state. We obtained the first context vector, and this Y0. All of this gives rise to Y1, the first word. Y1 would be the input to the next state. And S1 would be the input to the next state. And now the context vector would change. Now for the obtaining context vector, in the previous case, we used this S0. Now we'll use S1. S1 goes through and the same process. It passes through the MLP, gives me attention, gives me the scalar value. We put a softmax and finally we get a probability. And again, the same process is followed. But having said that, because S1 changes, H1, H2, H3, H4, all of them changes, the final context vector C2 would also change. So I have a changed context vector. This is in contrast to Sutskever's sequence to sequence paper, where context vector was fixed. So essentially, the idea of attention is to focus on something which we think is important. We or the model think is important. Like the model may focus on this stop sign. The model may focus on this people on the port. So that is what attention would do. And it's a fancy word for weighted average. Like we saw A11 times H1 plus A12 times H2, right? It's a weighted average of the hidden states. And came from this particular paper of Badano, the previous one that I introduced. And so this goes on. This still remains, the process remains the same and it goes on. So the next word is comiendo is like eating. So it has to focus at this point, and possibly A2, 3 will share the largest value among all these four elements. and so on and so forth. It goes so on and so forth. Okay. Now, a very generalized definition of attention comes from database. Like we fire a query, query is matched to key and outcomes. So suppose query matches with this key three, so outcomes value three, one particular value, right? But in general, the attention would have three elements: query, key, value, and what comes out. We first compute a similarity between query and key. So I will compute a similarity between query and this key, query this key, query this key. So I will have n similarities, and I will take a weighted average of the values. So whatever is this similarity of query with key one, that's a scalar value times value one. That value one is a vector. Similarity of query with key two is scalar times value two, so on and so forth. I will output a weighted average of these values. And what are the weights? They are nothing but the similarity of query with these keys. That's a generalized definition of attention. Um, so just in case, I will pause for a moment. If there are questions I can take, otherwise I can continue.
So I think that there is no query till now from the participants, so we can go ahead with
Yeah.
your presentation.
Okay. So there are various variants of attention. I mean, primarily self-attention and cross-attention. So I will begin with self-attention thing here. Uh, I will exactly clarify what do these terms mean. But let's say that, as I said, attention is a function of three things: query, key, and value. So suppose query is this sentence: the early word catches the worm. Same is the key, same is the value. Okay, I mean it's like a self thing. It's the same thing. Uh, so all these words, the model do not just interpret words. I mean, model transforms them into some real vector. So we'll have their embeddings. So we'll have some embedding for these words, uh, for the, let's say, the early, board, and so on and so forth. And the same embeddings are here, are here. So we can think this e as in some r d. They are some d-dimensional vector in real space. And they are passed through a linear layer. So if I have E, a vector, which is like this vector, it goes through a linear layer. So I have some linear layer, and out comes again another vector. Uh, yeah. So this is the embedding. So these are the weights WQ, and out comes this vector WQ transpose ETHE. So if I feed ETHE, then this is the weight. Sorry, this is the final vector that comes out. So we embed a word to obtain its corresponding feature, ETHE, and then pass through another linear layer, say WQ, and we get this particular feature vector. For each for each query, we will call this as tokens. These words are tokens. We'll call this as tokens. So each token go through a linear layer, parameterized by WQ, and out comes another real vector. Same thing for all the words. For key also, we have the word embedding ETHE, which goes through another linear layer. These are different. These weights are for query, and these weights are for key. These weights are for value. They're all same process goes on, but just that the weights are different.
Excuse me, sir. So can you take one question from the participant?
Yeah,
So Dr. Bhargavi is asking query key value. Are they always same?
not necessarily. So this is an example of self attention, but we have, say, cross attention where query could say, I mean, query could come from some place, and key and value can come from some other place. So they could be different.
Okay, sir.
Sir, one more question I want to ask from the previous slide.
Yeah.
No, the forward one. Yeah, from this slide. So if we calculate WQ transpose and like the embedding of the word for TAG, so this will be a single value, no, not a vector, I think.
So this is something like this. WQ is a matrix. It's a matrix.
So it will be a matrix of D cross D.
D
Okay.
cross D, right?
Okay. Yeah. Then okay.
Okay. So I mean, think of a fully connected layer, like we
Yeah,
have the.
actually, I got confused. Actually, I thought it was size 1 cross 4 or 1 cross the number of neurons. So
Yeah, it could be right. Unless we specify the dimensions, these could be confusing, right?
yeah,
But yeah, just that W is a matrix.
great. Okay.
Okay. Okay. Now a simple illustration. If we want to say find the attention weights for this particular word, say bird within the sentence. So the early bird catches the bomb. The process would be we had done this embedding. I mean, for each word, we had a word embedding that passes through a linear layer, which is nothing but this whole guy, this whole guy. This whole thing would again be a d-dimensional vector, would belong to RD. This whole thing again would belong to RD. Okay, both of them are d-dimensional vector. So I will take uh, this thing like going through the query weights, this thing going through the key weights, and I get d-dimensional vector, and I could take a simple dot product to obtain a scalar. Okay, to obtain a scalar, and I could do it for the word bird with all the other words, right? Bird with the early catches the bomb. Bird is missing, but bird should have been there, right? So all these elements, they are all scalar. They are all scalar, and we pass them through a softmax, and we obtain a vector of probabilities. So let's say this, we will call this as A1, we'll call this as A2, and so on and so forth. So that is what is written here. A1 VTHE. VTHE would actually denotes, yeah, this guy. This is VTHE. This is VTHE. So A1 VTHE plus A2 V early plus A3 V catches, so on and so forth. So this is the early, okay, spelling, and so on and so forth. So we have the weights like A1, A2, A3, and so on and so forth. These are scalars. They are all in real space, and these are vectors. They are all in RD. So A1 VTHE plus A2 V early plus A3 V bird, and so on and so forth, and that is the final value of bird, that I calculate. So this in another illustration, say I have a query, just one single query. I have 4 keys, so I will compute similarity of query with K1, Q with K2, Q with K3, Q with K4. I will get 4 scalar values. So again, think these are in RD, these are in RD, these are in R. They are just similarity scores. The way we would compute them is just via dot product. A simple dot product would do. But empirically, it is shown that the simple dot product, when scaled by the dimension of, so P is the dimension of Q or K. When it is scaled with the square root of dimension, it helps because Q and K, like if they are very large vectors, the dot product could blow up, could be very large. So scaling by the dimension could help. The square root of the dimension could help. So very simple similarity, like a scaled dot product. So these are Q transpose K1 divided by under root of dimension of either Q or K. That gives me S1, so on and so forth. And all this S1, S2, S3, S4, they pass through softmax layer, which is nothing but for A1, it will be ES1 by ES1 plus ES2 plus ES3 plus ES4. For A2, it will be ES2 by ES1 plus ES2 plus ES3 plus ES4, and so on and so forth. So I have this softmax. These are the weights. These are the weights. So I had a key vector, I had a query, I had a value vector, and I will just do A1 V1 plus A2 V2 A3 V3 A4 V4. That's it. weighted average. Okay. So this was one single query. But if I have so usually we have, just like I showed, there is a full sentence, right? So my query could be like a matrix. Okay, so if I have, say, say, the early bird.
Sorry, I don't understand.
Okay, sorry. Yeah, the early bird, and so on and so forth. So x1 could correspond to the, x2 could correspond to early, and so on and so forth, and xn could correspond to the last word, bomb. Okay, all of these words, they are in d dimensions. Okay. Uh, as I said, ETHC would be the embedding of the word, and which is a d-dimensional vector. So it's a d-dimensional vector. So we can take a d-dimensional vector, and for all the tokens we can take and stack them in a matrix. Now I have a matrix capital X, which is d cross n. I have n tokens. N words means n tokens. Each token is d-dimensional. So all this x1, x2, so on and so forth, they are all d-dimensional vectors. And I will pass them through a linear layer, WQ. WQ here could be of, say, in this case, I suppose it should be P cross D. It is P cross D, and input is X, so WQX, and X is my D cross N. So out comes my query vector, which is P cross N. Same thing for key, I will have its weight, WK, and for K, I will do WKX. Again, I get P cross N. Same thing for value vector, WV. WV would be in, this has different dimensions, R cross D. So WV times X, again, I get R cross N. So now we have compressed them into matrices. That is much more easier to operate. And the final attention equation that you will often see in the papers is given as this. These are the usual annotations. Z is the output of attention, and attention is a function of three things: Q, K, and V. Q, K, and V, which have these dimensions: P cross N, R cross N. And the final attention could be computed in this form: V, which is R cross N, softmax, and this whole thing is N cross N. I mean, Q transpose K. Q was my P cross N, and K was also P cross N. So when we transpose, we get N cross N matrix. So outcomes in Z, Z is in R cross N. It's a real, there are N tokens. Q was N, so that is like there are N queries. Correspondingly, there are N outputs, that is N values with dimensions R. So this is a compressed notation of whatever we did. Whatever we did, this thing. This is a compressed notation for the attention thing. So in comes N tokens, out comes N tokens. The number of tokens won't change. Okay. Let me show it more graphically. So let's say we have. So this is an example of cross attention now. So see, there are four query tokens and three of the key tokens. So what I will do, I have to take similarity of Q1 with all the keys. So Q1 with K1, Q1 with K2, Q1 with K3, Q2 with K1, Q2 with K2, Q2 with K3. So these are the similarities: E11, E12, E13, E21, E22, E23, so on and so forth. And then I have to take softmax. So I will take softmax along columns. Okay. I get these corresponding softmax columns. And once I have softmax columns, I would have a value vector coming from this thing. And the final output would be A11 times V1, A12 times V2, A13 times V3. So this output Y1 is corresponding to Q1. And for Q2, it's like A21 times v1, a22 2 times v2, a23 3 times v3, and so on and so forth. So in comes 4 tokens, out comes uh, four tokens. But note that because of attention has looked at all the elements, right? Q1 is looking at all the elements, Q2 is looking at all the keys, Q3 is looking at all the keys, Q4 is also looking at all the keys, and finally producing a value. Okay. I will go back to the self-attention thing. Self-attention, I have, say, 3 tokens, x1, x2, x3. I pass them through some query weights. I get their respective query tokens, q1, q2, q3. I pass them through the key weights, which give me tokens k1, k2, k3. And again, I will take the dot product. Like you can just do q transpose k. So, or otherwise think of it as q1, k1, q1, k2, q1, k3. We get the similarity. Pass these through a softmax, and again pass x1, x2, x3 through the uh, uh, value weights, and we get this value vectors. And finally, I get um, 3 tokens in and 3 tokens out. And what is the equation behind this? The equation is simply this output is nothing but z is nothing but v softmax, the same that I wrote under p. Right? So in this case, my v is some r cross 3, and q transpose k is 3 cross 3. I mean, this q transpose k is just this guy. Right? So I get a final 3 token vector as output. Okay. So one of the things with attention is that, let's say if I permute the input, I had x1, x2, x3. If I permute it, I have x3, x1, x2. So corresponding to x3, I will have the respective query q3, x1, q1, x2 gives this query q2. And same thing, x3 when passed through the key thing, it gives me k3, k1, k2. And again, I will compute the similarities q3, k3, q3, k1, q3, k2, and so on and so forth, and the softmax, and the value, and the final thing. So what we see is, previously we had y1, y2, y3. Now those values remain same. Okay, just that they are permuted. So now where x3 is there, I get y3. Where x1 is there, I get y1. Where x2 is there, I get y2. So they are permuted. Just like uh, in the order I permuted the input, the output also gets the same permutation. The values of the output don't change. They don't change because the remaining things remain the same. I mean, Q3 is the same. The these similarities would remain the same. Then the softmax things would remain the same. Value remains the same. So all the things are the same. It's just that their order is permuted. And we call this as permutation equivariant. That is, let's say S is self-attention. So if I compute self-attention and then permute, like in the previous case, like in this. Okay, we'll have to probably go way back. Yeah. So suppose I compute this full self-attention and then permute this output. This is one case. The other case is this. The other case is this running case where I permuted the input and compute the self-attention. So if I do self-attention and then permute, or first permute and then compute the self-attention, both are same. Right? Both are same. We'll call this as permutation equivariant. It's this attention is permutation equivariant. If you permute the inputs, the outputs permute in the same order. Okay, so essentially saying self-attention doesn't know the order of vector it is processing, but it is very crucial to know the order. Like we are eating bread, right? I mean, if I change the order, I mean, eating RV bread, I mean, that just doesn't make any sense, right? So the sequence is very very important. So that is broken by this thing called positional encoding. So say x1 is a vector, some d-dimensional vector, then we can concatenate it with another vector. This is called positional encoding. And then even if I permute input, that meaning even if I permute like this, x3, x1, x2, this remains the same. This doesn't change. We are not permuting this. I mean, this is the first token. So the vector that the vector that is this E1 positional encoding, that remains the same. So now see, I mean, even though we have permuted X, we haven't permuted E1. And this whole thing, I mean, this whole thing is no more the same. Right? Is no more the, is no more the same. So this breaks up the permutation equivariance, and essentially it tells the network, it tells the attention that there is some order attached to it. And there are various ways of computing E. Either a lookup table could do. Lookup table could mean that you already have some dictionary and you're picking up, or it could be learnable. Other things are fine. Okay. So there are few more building blocks that we need to know before we can compile all of them to obtain the modern day networks. The other concept is called masked self-attention layer. Uh, so this is the same thing, self-attention thing, x1, x2, x3. I have query tokens q1, q2, q3, so on and so forth. Usually in the NLP, the way the models were trained was like we are eating bread. So it's something like they have to predict the next word. So with some start token, they have to predict V. Then V goes, and then it predicts R. And then R goes, it predicts eating. And then eating goes, and it produces bread. So the models are trained like this to predict the next word. So it can see any past, but it cannot see the present. I mean, if it sees the present during encoding itself, it's very easy for the network to predict the next word. So in that sense, that is hidden. So it cannot look ahead. It can look in the past. It cannot look in the future. So supposing that x1, x2, x3, they're coming in sequence. So x1 can look at x1 only. X2 can look at x2 as well as x1 in the past. X3 can look at x3, x2, x1. So it looks at the entire thing. Now, how do we model this in the attention layer is Q1 with K1, because Q1 can see X1 and K1 is corresponding to X1. So it can, I mean, this is fine. This is fine. But Q1 is not supposed to see X2 or correspondingly K2. So in this similarity, this similarity is made as negative infinity. Q1 is not supposed to see Q3. This similarity is negative infinity. Q2 can see both of them, both of x1 and x2, so these are fine. But Q2 cannot see Q3, so negative infinity. Q3 can see all of them, so all these are scalars. Now, when we do softmax is like, for this guy, it will be e to the power minus infinity divided by some finite thing, non-zero thing. So it becomes 0. Same thing goes for this, same thing goes for this. So now see, these are zeros. So x2 and x3 do not have any impact for this y1. It's all derived from x1. For x2, v3 doesn't have any impact. Everything is derived from x1 and x2. But for x3, all these are going to contribute for y3. This is called masked self-attention, so that you don't look ahead, you look only in the current and the past. This is just an illustration of the same thing. Okay. Now another block is called multi-headed self-attention. So the self-attention that we talked about, this whole block, like x1, x2, x3, q1, q2, q3, and so on and so forth, and we get same number of tokens as output. We replicate this multiple times. The difference being that we had, say, w, q, k, v here. We will have, say, w, q, k, v prime. The weights are different. And we'll have w double prime, q, k. The weights are different. So all this, the output, although the input is same, x1, x2, x3, but the final output y1, y2, y3, they will differ because we have changed these weights. The query weights, key weights, and value weights, they are all different. typically there could be 6 heads or 8 heads. 8 heads has shown to be empirically more robust. So now we have individual heads, and these individual outputs will concatenate them. So this is R cross n. This is R cross n. This is R cross n. All of them, if I have 3 tokens like R cross 3, R cross 3, R cross 3, I will concatenate along the dimensions. So the final thing that will I have 3R cross 3. So I will take this y1, then this y1, and this y1. I will concatenate along the dimensions. So if this is say 512 vector, then I will have 512 plus another 512 and plus another 512. That will be the final 512 into 3 would be the dimension of my y1, this guy. Same thing I will do for y2, this y2 and y3. Okay, any questions so far? So roughly these are the building blocks of the attention, and I will move on to how
But
they.
actually, we have one question from one of our participant.
Yeah.
Which similarity measures can be used to find similarity between query and key?
It could be anything. I mean, it could be just plain dot product. I mean, as I showed right now. So if you have say query which is d-dimensional and key which is d-dimensional, you just do q transpose k. That's the dot product between them. That could be similarity. Otherwise, if you wish, you could do something like this on q minus k, and you could take a Euclidean distance. Euclidean distance or any LP norm is fine. That could also give you similarity between the two. Okay, I mean, this would give the distance. So you have to convert it to the similarity.
There is another query from Dr. Sophia. In the slide 84 or 84, you said there won't be a change in positional vector. I did not understand that. Could you please elaborate a little more?
Change. Sorry, I didn't get the question.
You said there won't be a change in positional vector.
So
I didn't understand that.
talking 83, slide 83, right?
84 he's talking
84.
about. Yes.
Okay, the question is still not fully clear to me. I mean, there could be some positional encoding. I mean, it's by default.
So he's talking about page number, slide number 83, E1, E2, E3.
Yeah. So, so see, I mean, one case is where you have x1, x2, x3. If you permute, you would get x3, say x1, x2, right? This is the thing. Okay. But the moment I have say appended these positional encodings, now even if I permute, my permutation looks like this: x3 e1, x1 e2, x2 e3. This do not change, right? This do not change. So in this case, the input is the same and is permuted. Now my input is not the same, right? What is my other input? It is x1 e1, x2 e2, x3 e3, right? Here the inputs are same. Like I mean, previously it was x1. Those things are same, right? But here, if you see, this whole is one input, and now see, it's not the same. Okay, but if you see in this case, this is x1, this is x1 2, but that is not the case anymore here. X1 e1, and now it becomes x1 e2. Okay. So in that sense, the input is that breaks the permutation equivariance.
So can you take one question from the participant?
Yeah.
Dr. Mohammed, can you please unmute yourself and you may ask? Please unmute yourself and you may go ahead with your question, please. Or otherwise you can type it out over here in the chat box. Okay, sir. We can go ahead with your presentation, and later on we can take
Excuse me, sir.
question.
Excuse me, sir.
Yeah.
Uh,
Yeah, I have asked the previous question. I'm Sophia. Hello.
Yeah. Yeah. I'm listening.
Yeah, actually, I didn't understand on the 83 the if the input is permuted.
Yeah.
So you said the example as we are eating bread. So I didn't get that x1 and x2 x3. So when you're permitting it like we are eating bread, the r comes first and like permuted permutation. So how
Right.
the position, even the position also the individual token also is getting changed.
No, 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 no,
So
no, no, no. The position is not changing. See, this is how I permuted x3, x1, x2, but I didn't permute this guy, right?
okay, but it is associated with each token, right?
No, 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 no. It's a positional encoding. So E1 denotes the first position. Now x3 comes at the first position, right? So it's associated with the position, not the value x3.
Okay. So
Okay.
the x1 is nothing but the each individual token, right? The
Each
value of each
individual.
token.
Exactly. Right. Right.
So it doesn't move with the associated position, right?
No, no. So the E1 is still at the same position E1, right? E1 is that is not getting permuted.
Okay, okay. It has to memorize that.
Uh, no, not necessarily. It's like suppose I fix this thing 100 010 001. So I mean it could be like this. I mean whatever you mean by memorizing, this remains fixed.
Okay,
This
okay.
doesn't change. If this changes, then we are back to this guy,
Right.
same guy, right? I mean
The
that.
permitting the input combinations.
Correct, right. So it won't break that equivariance. But
Okay.
in this case, E1 remains same as E1. It doesn't change. Even if you permute x1, x2, x3, E1 is still at the same first place. So that breaks this equivariance.
Okay, what is the objective of that if I don't change it? Like,
Yeah, so the neural networks, I mean, the attention mechanism doesn't understand the order, whereas the order is very much important. I mean, say we are eating bread, or I mean, if you permute it, it doesn't mean anything, right?
okay.
So on one side, we are eating bread is giving me some output, and if I
Oh,
permute, I still get the same output in the permuted sense. Okay? So
all
it
right.
doesn't make any sense to have have this thing.
All right. Thank you. Yeah.
Sir, let me confirm one thing with this positional encoding. We are not changing this because we that is why we are permuting it now. If we change the positional encoding, then there will be no sense of permuting the input, right?
Right? Yeah.
Okay,
Yeah.
thank you.
Okay. All right, that's good. That's good. So I will move on to the vision transformers. So there was. So I said that the sequence to sequence 2014 ICLR was the one which introduced the attention, and then came many good papers. 2016 and 2017 was another breakthrough. I'm calling it as breakthrough because if we call 2012 as breakthrough, where CNNs outperformed everything else, 2017 was the one which showed that attention, simple attention blocks outperform the other paradigms. So this was Attention is All You Need paper, 2017, very popular paper. And it showed that this whole network, and this is the encoder part, and this is the decoder part. If you use this is for the NLP community. Then this showed surprisingly excellent results. And I guess this has about more than 1.4 lakh citations as of now. So the classical thing remains the same. Like I have some text tokens which go through some embedding layer. I get embeddings. I have positional encodings. Either I can add or I can concatenate. Either ways is fine. And then comes this full block. Some of this is known to us like multi-headed attention, but the other things is not fully known. Okay, and this is the encoder, and encoder has a couple of more things, like instead of multi-headed attention, it has mask thing. And this arrows basically show uh, cross attention thing. But let me break it down. Let me start with the encoder part first. So this is my encoder. Okay, so let's say I have some x which is d cross n. Okay. So I'm not specifically talking about the positional encoding as of now. I will come to it a bit later. Okay. Now x, it goes through um, query weights, I get Q. X goes through key weights, I get K. X goes through value weights, I get V. And I compute this attention, V softmax Q transpose K by root P. Okay. Uh, and there is this residual connection. So whatever is the input, let's say my input is X, and I get some output at this multi-headed attention at this point. Some. Okay, so what this connection says that I do X plus Z, they're of the same dimensions. They're of the same dimensions. I do X plus Z, that is this at, and this bracket denotes normalization. This is layer normalization. I won't go into this layer normalization. I hope, I mean, either you know or you could figure out, or maybe just okay. So just like this, say suppose this is my linear layer across which I get the outputs. So for say if I feed one sample, if I feed one sample as input, I get say say Z1, Z2, Z3, and Z4. These are the outputs. So what I will do is I will just do Z1 minus this mean, like say summation I Zi by 4. So and divided by the variance of this whole thing, variance of Z. That is the mean of this and the variance of this. It's a square root. It's a standard deviation. So this is the layer normalization. Like I get all the activations, take the mean, and then normalize each activation. That is a layer normalization. Now this multi-headed attention, let me focus on this block first, the multi-headed attention. We have already seen, so something like I have X, I have say a value matrix, a key matrix, a Q matrix. It goes through, right? And I finally get V1. V1, K1, and Q1. I have X, I have another head. This is a parallel head where the value matrix is this, key matrix is this, Q matrix is this. And I get correspondingly V2, K2, K2, and Q2. So I have multi-heads means there are H number of heads. For each head, I will have its own key, K, and V. That is V1, K1, Q1, V2, K2, Q2, and finally VH, KH, QH. Each head is processing it independently. So for each head, I will compute its own attention thing. That is nothing but the scale dot product similarity, and finally I will get Z1. Right? So my Z1 is what? Is nothing but say V1 softmax 1 over root P Q1 K1. This is the output of the first head. Similarly, the output of hth head would be ZH is nothing but VH softmax of QH transpose KH by root P. So I have these many outputs. I have H heads, I have H attention mechanisms. Each is producing its own Z1, Z2, ZH. Right? And remember the dimension of Z was R cross N. Okay, my V was R cross N, and Z was also in R cross N. N number of tokens in, N number of tokens out, and the dimension is same as the dimension of the value vector, which is small r. And I will concatenate. So remember the multi-headed attention, we have H heads, they have H outputs, and all the outputs are concatenated along the dimensions. Okay. So when I concatenate, I will concatenate it like this: Z1, Z2. Each Zi is, remember, is this guy, R cross N. So if I say Z1, Z2, so on and so forth, ZH, this belongs to R, HR cross N. Okay, this is the concatenation. I get HR cross N vector. And they again pass through another linear layer. Okay. So I could call this linear layer as WO could be something like R, R cross D cross HR. Okay. So I could call this as WO, and this final, let me call this as final Z. WOZ. Okay. So I have input, which is HR cross N. I have this weight matrix D cross HR, and out comes a D cross N vector. Remember, my input was D cross N. So if I have to add Z, I have to finally have a D cross N only. So that is why all these operations, and finally we have a D cross N vector. So this multi-headed attention block. It gives me Z, which is same dimension as X, and I add back X and then do a normalization. So usually normalization, I mean, different normalizations are proposed like Rashnom and all, and they show uh, better robustness uh, plus the performance improvement. So this is the first part. This is the first part, X plus Z, and then layer normalized. Now I started from D cross N, ended back at again D cross N, right? And this goes through another feed forward network. So this is something like this, that this feed forward network, it will take a D dimensional input and project it to, usually it's something like 4D, and then come back to D. Come back to D. Okay. So if I have, say, some D cross 1 vector, it goes through, expands, and then comes back to D. So all these n tokens, D cross N, they go through this feed forward layer. And again, I would get a D cross N vector. Okay, so so this was my multi-headed QKV WOT concat, which gives me the final Z. I do X plus Z and then norm, and then put it back to a feed. So at this point, I have X plus Z. This. And put it back to the feed forward network. Feed forward network is one linear layer with some activation and then another linear layer. So I could write it as, if X is the input, I could write this whole network as W1 transpose X with some bias, and this is the ReLU. And then again another layer 2 weights, W2 transpose and layer 2 bias. Okay, so that is the whole operation of this particular block. I get this X plus Z normalized, feed it to this network. And again, so if suppose R was this output, then again at this point I would get, after this add and norm, I would get something like this. This is the input, that is this guy. This is the output, R. I will add R and again do a normalization. In comes a D cross N. R is also D cross N. So we can add it, no issues. This is just an MLP, right? So it's just like a batch of samples go in, batch of samples come out with the same dimension at, and then again do a layer norm. So this is called a transformer block. That's why, we keep on hearing the transformers. This is a transformer block. And there are n such numbers, n could be 6, 12, 24, or something like this. So this n denotes that this the same block is repeated. Could be 6 times, could be 12 times, so on and so forth. But all these weights that we are talking about, WO, WQ, K, V, they all would change. Okay, they are all learnable and they are all changing, right? Across different blocks. They are all changing. Okay, so I think this is roughly what I have mentioned. So this is the thing that I mentioned, that X plus Z we got. R is the output of the feed forward network. We add and then do a normalization. This brackets are denoting normalization. Okay. Any questions so far? That is roughly, that is basically the transformer block that we keep on hearing.
There is one question from Dr. Ahmad Hussain. Sir, what is the number of parameters for multi-head attention?
No. So each multi-head, each head has its own W, Q, K, and V. Okay, these three different weight matrices, and there are h number of heads, which is typically, no, I mean, typically h could be 8. They have shown that it is working best for them. So these many parameters, and so that is for the multi-headed attention. Yeah. So these are the number of parameters, and whatever be this WQ, the dimension of the matrix, accordingly you have the number of parameters.
Okay.
Uh,
Sir, this is the question that is there from the participant for the time being.
okay. So how much time do we have?
Uh, so it is up to 9 p.m. So
Okay.
if we want to proceed also, then we can extend a little bit.
Okay. Maybe I will proceed for 5 more minutes,
Uh,
and
uh,
if there are questions.
yes, 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 sir. Yes, sir. That is very much. Yes.
So if you just look at this sentence, the animal didn't cross the street because it was too tired. So if I look at this particular word, right, and so see, I mean, it has the attention corresponding to animal. I mean, the width of these lines, they show the attention. The more the width, the more the attention. So in that sense, it is able to understand that it has to focus to the animal. I mean, it has understood that yes, it is referring to the animal. Same thing here. The girl and the boy walked home. She, so it understands that she refers to the girl. The width of the line is again showing that the more the attention. Okay, and decoder part has couple of more blocks like masked, headed attention, and here is where I mentioned that, I mean, key and value they come from the encoder part, and this is the query. So this is the cross attention. So they are the changes. Like it has masked, multi-headed attention, and then multi-head attention with cross attention, and then feed forward network. So a new block, and this existing block, instead of just the plain self attention, it uses some masked attention. There are few more things, but I think those details we can't really you know, go through now. I had slides on positional encoding, but I think I will skip. So for the time being, just think that positional encoding is nothing but one hot encoded vector, right? So just like I said, 100, 101, 110 type of vector. Okay. So now coming back to the vision part. Coming back to the vision part. So uh, between 2017 and 2020, there were many attempts like bringing attention to the classical CNN networks, but they were all hacky. They didn't have much promising performance. And this paper by Dosovitsky came up in 2020, published in ICLR 21, and image is worth 1616 words. Uh, this changed the paradigm from CNNs to transformers in vision. In vision. So what he did was he first divided the image into patches. Okay, so I have these patches which are of size say 16 cross 16 cross three, I mean three channels. Goes through a linear layer, so I get some d-dimensional vector, typically 768, because I mean this is 768, so 768. Add some positional encoding, and that is it. Okay, that is it. And then have the transformer block, the same transformer block as I mentioned, and we have output vectors. So we could have n number of such transformer blocks and just repeat this. And finally, we could just, I mean, one way is we just pool them, like we just add them, take the average, and put a linear, take the average, and put a linear layer, and do a classification task. But the typical way it is done is they append a CLS token. So we have these tokens, which are the usual tokens. There is another learnable token, which is called CLS token. And corresponding to this, again, we'll have an output. And that output is basically projected to a linear layer and to a softmax, and which could be trained via cross entropy loss. Uh, so he made minimal changes. Almost, I mean, all these transformer blocks, everything remains the same roughly. I mean, positional encoding, this encoding, all. So just think that this is a word. Just think this is a word, right? This is a word which, and we get the word embedding, positional encoding, and that is it. And then just apply the NLP transformer and an encoder block of the transformer. So that was it. I mean, this is a 224 image. We divide into different patches. In this case, there are 196 patches. All of them go through a linear layer and give us a 68 dimensional vector. We had positional encoding, and then there are transformer encoders, finally leading to a MLP head for classification purpose. Uh, yeah, so that was the thing. Okay, so I have quite a few more slides, but just to mention that uh, since VIT, many more advances have happened on the transformer side, and roughly now many vision tasks are done via transformers only. And the encoder decoder thing that I showed, the decoder is what I mean. ChatGPT is built upon. Of course, I mean it's much more smarter than that. But the building blocks are the decoders. From this attention is all you need. Uh, and the encoder part forms the base of many models like BERT, which are basically text encoders. So if you want to encode text, it uses a BERT or a variant, and BERT is nothing but that encoder part. If you're using GPT, I mean ChatGPT or something, it's built upon the decoder part. And many of the vision tasks, they are built upon the encoder transformer encoders. Um, so it's not a logical conclusion, but I would be more than happy to take up any questions rather than going with more slides.
Okay, sir. So there is one query from Dr. Bhargavi. So which software application have you used in slides to explain the transformers layer wise by example?
Uh, so layer wise, I mean, you mean which?
You can
I didn't get. I mean, this layer. No, sorry. I mean, which? You mean this layer wise thing or?
uh, can you, Dr. Bhargavi, can you please unmute yourself and you may ask directly or you can
Sir,
interact.
can you please go to the next slides? Next slides, please. Next slides. Yeah, please stop before decoder. Yes, sir, this one. I'm
The
interested
previous
to
one, I guess.
know what application you have used.
No, no. So this is by this guy. So I have picked from uh, this guy. So they have. I should have a link over here, but probably it's missing. But this figure is from elsewhere, and I didn't create this figure.
Okay. So any other?
Probably I
eh,
missed that link.
Yes, sir, please
okay,
do share the link.
Let me check if I have. Yeah. So meanwhile, I can take up the other questions. Let me just check.
Uh, there is another query from Dr. Kirtika. So, will vision transformers help to choose sampling rates?
To choose sampling rates. I mean, sampling rates as in, I didn't get the question. I mean, sampling rate, you're probably referring to signal processing, right?
Dr. Kirtika, can you please unmute and you may directly interact? Is it possible from here, Dr. Kirtika? You can interact directly about your query. Okay. Again, Dr. Kritika typed that adaptive sampling in compressed sensing.
Adaptive sampling in compressed sensing. Okay, I mean, so long as you have any parameters that are learnable, you could, transformers could be used.
Good
But
evening, sir.
Yeah, yeah. Good evening.
So
Yeah,
this is Kritika, sir.
yeah.
Sir, I just want to know whether this vision transformers helps us to choose the sampling rate in compressed sensing.
Okay, this okay. I don't. I mean, I don't think I fully understand what are we trying to do. Um,
Actually, with the help of the vision transformers, we'll be able to identify the patches which has got the maximum features. Is that is possible?
uh, no, I mean, straight away, I don't think it could be straight away extended. Like, see, the way the transformers are trained, I mean, especially the vision transformers, it's like, uh, I mean, think of supervised setting where you know that there is an image. An image is of an object, say a chair or a table. So you have a label, right? So it's supervised that ultimately we are telling the network that this chair is the input image and it is a chair. So you have to classify it as a chair. That is what we are telling, and the network is learning. But in your case, I don't think such supervision is, such supervision is available. So there could be a roundabout way, but I don't think I fully understand the problem. I mean, if you feel you could write to me, I can think about it, but probably I need a little more think about the problem.
Okay, thank you, sir.
Yeah.
Okay, so there is another query. Transformers have been used in image and videos nowadays, but what are the uh, niche area which respect to? So can you please unmute, Dr. Arpan? Can you please unmute and you can ask?
Yeah, hi sir.
Yeah.
So, sir, I
Yes,
just
please.
wanted to ask, like, for video task, what are the main challenges that are still needed to be solved for, like, transformers with respect to transformers? So, the
Mhm.
niche areas that are there
Okay.
nowadays.
Yeah. Yeah. So the if you just look at the complexity, the attention matrix that we are computing, that Q transpose K, it's like of the order of n cross n, that is number of tokens cross number of tokens, right?
Yeah.
Now, just for the last example that I showed, the number of tokens are 196. So the attention matrix, the complexity grows, it's of the order of 196 squared. And you have many, many such transformer blocks. So it's quadratic in the number of tokens. Now, when you bring in the temporal dimension, the frames, then for each frame, possibly, so it's getting multiplied. It's linear in number of frames. So for each frame, you have order of say quadratic complexity. For each frame, it grows. But we cannot treat frame as I mean frame as independent. So there are various ways by which we do this patches. Like I mean, we could take a cube. Uh, think of this patch which is extending across time. So that's a cube. Or otherwise, we can take individual patches and fuse at a later stage. So there are various strategies. Either build a spatiotemporal attention, which is like a cube, or use a spatial thing. I mean, for each frame you're doing independently, and then fusing it later. For each frame you get some encoding. So you have again n number of frames, n number of tokens later. So first you have a spatial attention, and then you will have a temporal attention for the frames output would fit to the temporal attention part. But again, there are various combinations. So and that means that you have to check the complexity. The cube might have a lot of complexity, and the space, if you break down the space and temporal thing, the complexity might reduce, but you're not processing probably. I mean, what is the right fusion? Should I just go through the space and then fuse at the time thing? So that's not very clear, right? Where should I fuse? If I go through all, the complexity might be very much. If I go through individually, then I'm not sure what is the right position where I should fuse. So those are some of the problems that is still. I mean, some of the video attention, some of the papers which specifically talk about spatiotemporal attention, talk about especially about the complexity of these.
Yeah. Thank you, sir. Thank you for the insights. Yeah.
Uh, there is one more query from the participants. So, what are the challenges of transformer modeling for image-related applications?
Um, so some of the challenges were like this: that if you see CNN would take a full image, and it narrows down, right? I mean, it goes down. So the number of channels increases, the spatial resolution goes on decreasing, and finally you get a vector and you operate on that. But look at the transformers. The number of tokens in is the same number of tokens out. So there is no reduction at any place. So as a follow-up of VIT, Swin came up from Microsoft, uh, which tried to handle this problem that there is a hierarchy in CNN, and how do we translate that hierarchy to the transformers? So some of those problems are still
in CNN. We are using convolution, sir, for image applications. Can we use the convolution technique in transformer modeling?
well, nothing stops us, but it's so that the transformers have beaten CNNs.
So presently we are using for text conversion transformers for self attention. I think.
No, not for text. I mean, text was done, in 2017 itself. And since 2020, people have
language processing. That is from one language to other language.
Correct. Yeah. I mean, language processing, or just in case, language translation processing or anything.
Yeah.
But since 2020, people have moved to transformers.
For entire thing, we are only converting text into text. No, sir. One language of text to another language or sentence, or like that. But if you take image, there we have to consider pixels.
Right.
There we have to get the features by using convolution technique. That is, in CNN, the different layers are there.
Okay. Let me just, share this.
So here I am asking is how we can change transformers to predict image and recognize image or object.
Yeah. So that was this where I sort of ended, right? Okay.
Then if we implement this technique, convolution technique in transformer modeling, we can avoid CNN, no, sir?
No. So, okay. So see, the primary thing why we moved to transformers is they have different capability than CNNs.
Yeah.
Right? And transformers showed that they can beat CNNs.
Yes.
So, now going back to CNNs, that I'm not sure. I mean, there is no motivation to go back to CNNs.
But here we are using image, no, sir?
Yeah, that is fine. So that is what this paper did, right? This paper was another breakthrough in the vision, that it created these patches, and then the patches go through linear layer, and that is it, right? Finally, you have an embedding. In the case of text, it's the same thing. You have a word, goes through some processing, and you get an embedding. Ultimately, that embedding feeds to the whole transformer block.
Yes, sir.
So I keep the transformer block same. I have this patch, convert this patch to some embedding. Now it is same as, now it doesn't matter whether input was text or input was image. Both of them are converted to some embedding, right?
Okay. Okay, sir. Thank you.
Yeah, thanks. Okay, I see some raised hand.
If you want to take up this question, then we can, sir. So please unmute yourself and you may interact with Dr. Subramaniam. Please.
Sir.
Yes, Dr.
Sir.
Yeah.
Can I? Sir, but
yes,
only
please,
when the
please.
thing is, because when we are converting into patches, that indicates that transform works only with the 2D images.
Mm-hmm. Right.
So that is one of the, and plus the data set requirement is also too much high, over here when you compare to with the CNN.
Yes, right. Yeah. That is true.
Yeah, that is one of the drawback, no? Because it works, it gives good accuracy with the transfer only with the 2D patches. But the CNN, we can have the 3D net as well as the 2D networks.
Yeah, fair
And
enough.
color
And
image also we have to process it. Lot of data set we have to use for recognition and object recognition. But how far transformer modeling is prefer for image recognition, I think.
yeah, pretty much. See, as I said, right? Come 2020 now, only transformers are used.
Yeah.
They have thrown away the CNNs.
Yeah.
Whether you talk about 2D, I mean, image is like 3 channel also, no problem. As I mean, this slide that clearly shows that I'm crossing a color channel, 3 cross 16 cross 16. If you want video transformers, yes, no issues. Just take a cube, right? So it is something like 3 cross 16 cross 16, cross the number of frames. Pass it through a linear layer, you get an embedding, you process a video.
Yes.
Okay.
Okay. Thank you.
Thanks, sir.
I think uh, so. You have answered all the queries that been raised by the participants. Okay. So thank you, sir, for today's session for RNNs to attention. So which is very insightful and engaging. So you began discussing the fundamentals of RNNs, then introduced attention mechanism, explaining their evolution. Key topics like self-attention, multi-head self-attention were covered in very detail. So providing a clear, very much clear understanding to all of us. So thank you, Dr. Subramanian, for delivering such an enlightening session and for simplifying this complex concept to us. Thank you very much, sir, for
Thanks for having me.
this. Thank you so much, sir.
Yeah. Okay. Okay. Yeah.
Okay, okay, sir. Good night, sir. Good night.
Good night. Yeah. Good night. Bye.
Good night.
Thank
Okay, so good night, all. So